história que começou em 1963. Com décadas dedicadas ao desenvolvimento de processos, produtos e embalagens, o Instituto de Tecnologia de Alimentos não mede esforços para se manter como referência no setor alimentício, não só no Brasil, como no mundo. Por entender a importância da inovação e segurança de alimentos, bebidas e embalagens para o consumidor, o Itaú pesquisa e presta assessoria técnica, visando a eficácia e padrões mínimos de qualidade. Além de estar atento aos diferentes perfis de consumidor, o Instituto atua sempre com ética e respeito ao meio ambiente, priorizando a análise crítica para acompanhar a evolução tecnológica e de mercado. As atividades do Itaú são divididas em 3 grandes áreas. A tecnologia é desenvolvida e aplicada nas unidades especializadas em carnes, cereais, chocolates, balas, confeitos, produtos de panificação, laticínios, frutas, hortaliças e engenharias de processo. A ciência e a qualidade são prioridades dos laboratórios de análises químicas, físicas, sensoriais e microbiológicas. A embalagem é o foco dos setores especializados em materiais metálicos, vidros, plásticos, celulósicos e para distribuição e transporte. E o conhecimento vai além dos muros da instituição através de artigos, publicações e eventos. O Itaú valoriza as pessoas que são força de trabalho e razão de existência. Por isso, está presente em importantes programas de governo que abrangem todas as classes e diferentes gerações. São décadas de constante reinvenção, aprendendo e ensinando, décadas de reconhecimento com a bagagem do passado e a modernidade do presente. Com funcionários qualificados, clientes, parceiros e fundações de apoio, o Itaú tornou-se fundamental no setor de alimentos, bebidas e embalagens.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years' experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.
Uma história que começou em 1963. Com décadas dedicadas ao desenvolvimento de processos, produtos e embalagens, o Instituto de Tecnologia de Alimentos não mede esforços para se manter como referência no setor alimentício, não só no Brasil, como no mundo. Por entender a importância da inovação e segurança de alimentos, bebidas e embalagens para o consumidor, o Itaú pesquisa e presta assessoria técnica, visando a eficácia e padrões mínimos de qualidade. Além de estar atento aos diferentes perfis de consumidor, o Instituto atua sempre com ética e respeito ao meio ambiente, priorizando a análise crítica para acompanhar a evolução tecnológica e de mercado. As atividades do Itaú são divididas em 3 grandes áreas. A tecnologia é desenvolvida e aplicada nas unidades especializadas em carnes, cereais, chocolates, balas, confeitos, produtos de panificação, laticínios, frutas, hortaliças e engenharias de processo. A ciência e a qualidade são prioridades dos laboratórios de análises químicas, físicas, sensoriais e microbiológicas. A embalagem é o foco dos setores especializados em materiais metálicos, vidros, plásticos, celulósicos e para distribuição e transporte. E o conhecimento vai além dos muros da instituição através de artigos, publicações e eventos. O Itaú valoriza as pessoas que são força de trabalho e razão de existência. Por isso, está presente em importantes programas de governo que abrangem todas as classes e diferentes gerações. São décadas de constante reinvenção, aprendendo e ensinando, décadas de reconhecimento com a bagagem do passado e a modernidade do presente. Com funcionários qualificados, clientes, parceiros e fundações de apoio, o Itaú tornou-se fundamental no setor de alimentos, bebidas e embalagens.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years' experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.
Good morning, America. Good morning, afternoon. Good afternoon, Europe and Africa. Good evening, Asia and Oceania. Well, we are pleased to open the Latin American Subcommission of the International Commission on Microbiological Specifications for Foods webinar entitled Update on Food Safety. I am Bernadette Franco from University of São Paulo, Brazil, and together with my colleague Miguel Sassopoulos from University Santa Maria, Chile, we will chair today's webinar. Let me start introducing the other members of the Latin American Subcommission who organized this webinar. You can see them in the screen. Marta Taniwaki from Brazil, who was the main organizer of this webinar. Then Santana Lidia Leon Afaro from Peru, Janete Luna from Colombia, Francisco Garcés Vega from Colombia, Ana Karina Carrascal from Colombia, Silvia Raffelini from Argentina, Maria Isabel Gabaldon from Venezuela, Cristina Lopes, Uruguay, and Dora Marta Gonzalez, also from Uruguay. We have also with us Pilar, who was a previous member from Venezuela. This webinar comprises 3 modules with talks presented by the members of ICMSF. I would like to ask the Latin American Subcommission members to switch off their screens. As I said, this webinar comprises 3 modules. 2 modules, today and tomorrow, are related to ICMSF food safety principles, presented in ICMSF Book 8, Use of Data for Assessing Process Control and Product Acceptance. These books are available in English, in Spanish, Portuguese, Japanese, and Chinese. The 3rd module, on the day after tomorrow, will be focused on COVID-19 in the context of food safety. We would like to take this opportunity to acknowledge our sponsors, the companies 3M and Merck, and the Food Technology Institute, who is hosting this meeting, and the Food Research Center of University of São Paulo, who is giving technical support. Their support was essential for the success of this webinar that has almost 1,500 registrations from Latin American countries and also other parts of the world. I will start our webinar introducing Professor Marcel Zwittering, the chair of the ICMSF, who will tell us the history and achievements of ICMSF. Dr. Marcel Zwittering became the chair of ICMSF in 2020 and is a member since 2005. He is professor in food microbiology at Wageningen University in the Netherlands. His research subjects are in the domain of food safety management, risk analysis, fermentation, detection and hygiene, ecophysiology, and functional genomics. He is editor of the International Journal of Food Microbiology and member of the editorial board of the Journal of Food Protection and International Journal of Microbiology. He is also active in many national and international expert bodies. Please, Dr. Zwittering, you can start.
Thank you very much, Bernadette. So thank you very much, and very much welcome.
That's nice.
Was some nice music. I don't know where it was coming from. Thank you very much, Bernadette, for this kind introduction. I hope you can see my screen. You can see it well? Mm-hmm. Yeah. Okay, so like Bernadette already mentioned, last year I became the chair of the ICMSF, and I would like to start with acknowledging Martin Kool, who has been the chair for the last 20 years of the ICMSF, and that is a great achievement that I will not be able to surpass, because there is a rule also that we have to retire in the ICMSF, and for me there is not any more 20 years to go, but I will do my best in the coming years. Also, I should acknowledge Martin because I borrowed some of the slides that he prepared, and I will give a very short introduction of the ICMSF. The first, it was first difficulty to get to the next slide, but the ICMSF is a committee, like Bernadette already mentioned, that produces books, it produces position papers, and it gives advice to governments, to Codex Alimentarius and to the FAO WHO. And the ICMSF is a daughter organization of the International Union of Microbial Societies. And also, that is again a daughter union of the International Council for Science. So that is how we are related to international organizations. So the ICMSF consists of 20 food microbiologists from 14 different countries in the world. And the people in the ICMSF have a very broad professional background, from epidemiology to methods, to food products, to risk assessment. So a broad professional background in the domain of food microbiology. The people are selected based on their competences and their technical expertise, and we are not national delegates. So the countries where people are selected from we try to have, of course, a regional distribution, but in principle, we mainly look for the technical expertise of people and how they fit in the team, and we are not a national representative. Apart from the people that are members of the ICMSF, we have also an extensive network of consultants and experts that we invite in our meetings. All the work that we do is voluntary and without any honoraria. And it's also very important to realize that we do give recommendations, we write books, we write position papers, but all our recommendations, as the word already says that are recommendations, they do not have an official status. If a government, of course, make use of these recommendations, then they can become official. But all recommendations have no official status. So if we look at the history of the ICMSF, it started in the 1960s, in 1962 to be precisely. And in the beginning years of the ICMSF, it was mainly focusing on microbiological methods. At that moment, methods were very diffuse and not well defined, and the Commission worked a lot on standardizing methods. Also, quickly, they began to work in the domain of hazard analysis critical control points and in streamlining the process of hazard analysis critical control points and make that the solid system as it is today. Also, quickly, the ICMSF started to work in the domain of sampling plans. Later on, we developed the FSO concept and together with the ALOP concepts. And that is all used still nowadays, the methods, the hazard sampling plans, the FSO concept within risk management. So that is the domain that we are working in. And looking towards the future, we are now looking also towards food safety of the future. So how can we still produce sufficient food for our planet in 2050 with all the issues of climate change and sustainability? So that is the domain where we are now still working. But of course, we are also still focused on hazard, on methods, on sampling plans and the FSO concept. So you see slowly an enlargement of the domain that we are working in. So you see here a picture of the Commission in 1969. So it was one of the first meetings, maybe the fifth meeting or so. And this was one of the annual meetings. And you see here the Commission members of those days, also a lot of founding members of the ICMSF still, but also many experts and consultants. So not all the people on this picture were members, about half of the people were members, and the others were consultants and experts that were invited in that meeting. So I have here a second picture, you could say 50 years later, because this was our 50th meeting. This was a meeting in the Netherlands. So it was 4 years ago. And like many of the meetings and also this meeting today, the last meeting in 2020, of course, was for everyone in their own cocon, and we did the meeting fully in Zoom. Hopefully next year we can again have a meeting where most of the people can be present and we can also physically meet each other. Bernadette already mentioned that the Commission produced a lot of books, and she mentioned also that these books were translated in Portuguese, Spanish, Japanese and Chinese. And that is in many cases the work of our subcommissions. And these subcommissions are very useful for the dissemination of our work, but also they bring information to the Commission, and they do the translation work, and also they do organize all kinds of events. We also produced lately 19 YouTube movies, and also, as you can see here, these YouTube movies, they are also subtitles, and also the people from the subcommissions are very active in making translations of the subtitles in Spanish, Chinese, Japanese and all kinds of other languages in our world. But apart from having these books, the position papers and these YouTube movies, of course, today also we have, or today, tomorrow and the day after tomorrow, we have a webinar, which is organized by the Latin American Subcommission. And this is, of course, again, a very nice way of diffusion of the work. And of course, COVID is a horrible disease. There is a lot of problems that we have nowadays in our world, but there are certain good things of this, because the Latin American Subcommission could organize this meeting, and there were 10 ICMSF members willing to now come to South America, you could say. Normally, if there is a meeting like this, that maybe 2 or 3 Commission members will join. But in this case, there are 10 people joining the meeting. On the other hand, also the dissemination towards the rest of the world is great, of course, because if it would have been in South America, not a lot of Europeans and people from Australia and from the United States would come to this meeting. But now we have almost 1,500 subscriptions from mainly South America, but also from many other parts of the world. So it is a very big disappointment that we cannot meet each other really physically. But of course, it's a great asset that now we have a lot of members together, a lot of members from the Latin American Subcommission, but also a lot of participants from all over the world. So to conclude the work of the ICMSF, it is a long-standing commission. It is 1 year older than myself. Also, it has produced all kinds of books, works, ideas that have a big international impact. So we could say that the ICMSF is making good quality products with a long shelf life. And I hope we will keep on doing that for a long time. But also, again, this webinar is now broadcasted, but it is also broadcasted currently at YouTube, but it will also be available for the future on YouTube. And again, hopefully for the coming 2-3 days, we have good quality products, but also with a long shelf life that they can be used all over the world for a long time. So thank you for your attention for this introduction of the ICMSF.
Thanks, Marcel Swietering, for your very nice introduction of ICMSF. I would like to inform the audience that the questions for the speakers can be forwarded to them using the link in the bottom of the YouTube screen. If you scroll a little bit lower than the image, you'll see a link for the questions. Okay, let's start the first module of the webinar. As I said, focused on use of data for assessing process control. We ask you to take active participation, sending us your questions. We will do our best to discuss them after each session. The first speaker is again Dr. Marcel Swietering, who was already introduced to the audience in the beginning of the seminar. Please, Dr. Swietering, you can start. Your time is from 9:15 to 9:45. Please, the floor is yours.
Thank you, Dr. Franco. So the first presentation is the comparison of different types of sampling plans. And why do we have so many different types? So why do we have different types? Einstein has said everything should be made as simple as possible. So why not have simply one type of sampling plan? However, Einstein did not say everything should be as simple as possible. He said everything should be made as simple as possible, but not simpler. The reason is our world is not black and white. We have all kinds of different types of microorganisms that we can measure in a sampling plan. We can have, for instance, indicators, for instance, hygiene indicators. Also, sometimes we are interested in toxinogenic organisms or infective organisms. Also, in certain cases, the target group of a food product is the general population, or it can be infants or even medicinal food. And of course, then it would be good to have more strict microbiological criteria. Also, the place where we can take our sample can be on a different place in the food chain. It can be, for instance, before inactivation, or it can be after inactivation. It can be a product that does not support the growth, or it can be a product where microorganisms can grow. So in certain cases, if I'm advised on sampling plans, then people ask me the question, I work with cocoa. How many samples do I have to take? Of course, that is a very simple question, but it's a very difficult answer. And you need first to ask a lot of other questions. For which pathogens are you interested? In which place of the food product are you targeting at? Is this product specifically meant for infants, etc., etc.? So all these questions need to be gone through if you are interested in a sampling plan. So it's not black and white. We have 50 shades of red. We can, for instance, in the cacao, determine the total plate count. That can give us some indication of the hygiene, but especially for cocoa after the fermentation, for instance, you expect very high levels of microorganisms. That does not say that the product is unsafe. It has been a fermented bean, and then it is expected that there are many organisms. If, of course, after the roasting, we have a very high total plate count, that is, of course, indicating maybe potential hygiene problems. You can also look at mesophiles. You can also look, for instance, at Enterobacteriaceae. That is already going a little bit more towards, you could say, pathogenic microorganisms. You can also measure in a certain food product the number of Bacillus cereus, and that is a pathogenic microorganism. You can also look, for instance, for Campylobacter or Salmonella in raw poultry. But this is a raw product. You expect that sometimes these pathogenic organisms can be present, but after the sampling, there can be still an inactivation stage. So your criteria might be less stringent than if we would not expect a cooking process afterwards. We can also have Salmonella in a ready-to-eat food. There is no heating anymore afterwards, for instance, in chocolate. And so you expect that if the organism is present, the person can consume the organism and get ill of it. And of course, if the Salmonella is present in powdered infant formula, which is a product specifically targeted at small babies that are much more vulnerable for pathogenic organisms, the criteria need to be even more strict. So you can see there are all kinds of different questions that we can ask ourselves if we are developing a sampling plan. And we need more stringent criteria for Salmonella in powdered infant formula than we would, for instance, have for a total plate count on vegetables. If we are going to set specifications, then often politicians, consumers, and maybe even the management of a food company would say, it's very simple, we want to have zero risk. But like I said, black and white does not exist. You can communicate about this on Twitter, but zero risk does not exist. A little bit better definition is already zero tolerance. That is already saying, okay, we do not tolerate any sample to be above a certain level. We can also define the criterion as, for instance, in a food product, absence in Listeria monocytogenes. Still, this is a little bit better defined, but not yet enough, because we should say, no, it's not absence of Listeria, it's that I did not detect Listeria. It's already a little bit better specified. But even it would be better to say Listeria monocytogenes was not detected in 25 grams. Or maybe you take 5 samples of 25 grams and say Listeria monocytogenes was not detected in 5 times 25 grams. This is a criterion. This is not saying that there is zero risk, but it is specified that you don't detect it in these 5 samples. For Listeria monocytogenes, there can also be for products where we have no potential growth, that in certain regions of the world we can say if you prove that the level remains below 100 CFU per gram during the shelf life, or for no growth products that the level is below 100 CFU per gram, and since there is no growth, it will never go above that limit. That could also be a criterion. And so this is again a well-defined criterion. So these are all examples of specifications. But we should say we are the International Commission on Microbial Specifications for Food, but one of our main messages always is that control of a product and a process goes with a validated hazard plan. And it's not by the criteria that you really control the risk. You verify the risk, but you don't control it. Since in order to have really a solid food safety management system, the first thing you need to do before asking how many samples do we have to take is that you need to have your prerequisite programs under control. You need to have a good manufacturing practices and good hygiene practices. If these are under control, you can start with your hazard plan. In your hazard plan, you have to validate your critical control points. And if you have validated your critical control points, you can start monitoring the critical limits in your process line. And if this is all under control, I would have trust in your food safety management system. This is how we control food safety. However, we always want to have some additional certainty, and therefore we have some verification with microbiological criteria to really verify that everything is going as it is intended. So this last part, that are the sampling plans, but it is, you could say, the last part of your food safety management building. Not the most important one, but it is the add-on verification. And if you would only have your verification and only have your microbiological criteria, so if the food safety system would only be based on testing, it has about the strength of a house of cards. And this will drop down rather quickly. So definitely do not forget the basis of your food safety management system. So I mentioned there are all kinds of sampling plans. And therefore, I'm going to explain you now different types of sampling plans. We do have qualitative sampling plans and we have quantitative sampling plans. So that is one distinction. A qualitative sampling plan is, for instance, absence in 25 grams or absence in 10 grams. So The qualitative plan is presence or absence, and for that you have to define also a quantity where you look for the organism. And to say it even better, it should not be absent in 25 grams, but not detected in 25 grams. We also have quantitative plans, and in a quantitative plan, you really count the number of organisms, like the example that I mentioned for Listeria monocytogenes. The level can be either below 100 CFU per gram or above 100 CFU per gram. So that is a quantitative limit. So we have a quantitative limit in a quantitative plan. Well, in the qualitative plan, it's a detect or non-detect. We also have 2-class plans and 3-class plans. So a 2-class plan can either be a presence-absence test, because presence-absence is always 2 classes. So you have either organism detected or the organism not detected. But also the quantitative plan for smaller than 100 CFU per gram and bigger than 100 CFU per gram is a 2-class plan. It's either below 100 CFU per gram or above 100 CFU per gram. We have 2-class plans, but we also have 3-class plans. And in 3-class plans, you have 3 classes. So we have 2 limits. One limit is, for instance, 500, and the sample can be below 500. The second class is below, for instance, 500 and 5,000. And the third class is above 5,000. So we have 2 limits, what is called the small m and the big M. And if the data are below the small m, we are in the first class. Between the 2 m's, it's in the second class, and above the 5,000, above the big M, it's in the third class. These criteria can be used as food safety criteria or as process hygiene criteria. So if we only look at the hygiene and determine the hygiene, it can be, for instance, in the environment, it's a process hygiene criteria. If we detect salmonella in powdered infant formula, that's really clearly a food safety criterion, really focused at food safety. That is really an indication that something is wrong and that a product is unsafe. So if we have 2-class plans and 3-class plans and qualitative plans and quantitative plans, we can also accept a certain number of samples to be positive, and that is the C value. The C value can be 0, then we do not accept any of the samples to be positive, but C can also be not equal to 0. So we have all kinds of possibilities, especially for the 2-class plan. The 2-class plan can be qualitative or it can be quantitative, and C value can be 0 or it cannot be 0. So that gives us 4 possibilities. Fortunately, for the 3-class plan, there is only one possibility, because a 3-class plan is always quantitative, because we have 2 quantitative limits, because a qualitative plan is always 2-class, because we have only presence or absence. And in the 3-class plan, since we have 3 classes, the C value always is not equal to 0, because we always accept a certain number of samples between the small m and the big M. Because if we would not accept any value between small m and big M, the C value would be 0, and it would return to a 2-class plan. So a 3-class plan is always quantitative, and the C value is never equal to 0. So now let's look in our legislation to examples of these type of plans. And I will go into detail for these plans later as an example. So we have salmonella in powdered infant formula. That is a 2-class qualitative plan where we do not accept any of the samples to be positive. A 2-class plan where we accept certain samples to be positive, Antibacteriaceae and PIF. And this is a process hygiene criteria, not a food safety criteria. It's not a pathogenic organism, it's an indicator of pathogens. We also have a 2-class quantitative plan, Listeria in no-growth RTE products in the Codex guidelines. We have in Europe also a 2-class quantitative plan where C is not equal to 0, and that is Campylobacter and broilers. And for instance, mesophiles in powdered infant formula is a 3-class plan that is quantitative, where the C value is not equal to 0. So for all these 5, I will now show really the sampling plan that is written either in the Codex documents or in the EU documents. So we have here a food safety criterion for powdered infant formula, so it's specifically targeted at the pathogenic organism for a population that is very sensitive, infants, and therefore it's the most stringent plan that we do have in our legislation. So in the Codex legislation, it says that for salmonella, we need to take 60 samples of 25 grams. None of these samples is accepted to be positive, and also the ISO method that you have to use is represented. So this is a qualitative plan. It's presence or absence in 25 grams. It's 2-class because it's either detected or not detected, and we do not accept any of the samples to be positive. So this is a food safety criterion. But also in the same codex documents, we have a process hygiene criterion for antibacteriaceae. There, 10 samples have to be taken of only 10 grams, so not 25 grams. So it's a more lenient criterion than for Salmonella, because you do not take 60 samples but 10. And also, you do not take 25 grams but 10 grams. And also, we accept 2 of these samples to be positive. So it's a much more lenient program than for Salmonella, because it's more an indicator. And this is a very useful criterion, because sometimes you will find 0 antibacteriaceae in your 10 samples, sometimes you will find 1, sometimes you will find 2. And this is already, you could say, an orange light. You know that something is going on. Maybe it's better to start cleaning. So it's a good indicator of things that go wrong, but it is not, it's still compliant with the criterion. Here we have again a food safety criterion that is quantitative, 2 class, and C equals to 0. 5 samples have to be taken. The limit, the quantitative limit is 100 CFU per gram, and none of the samples is allowed to be above 0. So this is a codex document for Listeria monocytogenes in ready-to-eat food products that do not support the growth of the organism. We have also in the EU a process hygiene criterion for Campylobacter, which is quantitative. It is 2 class, and the C value is not equal to 0. So this is in broiler, so these are products that still have to be cooked. So we do accept that sometimes Campylobacter is present at higher levels. It sometimes can be present, it can sometimes even be present at higher levels. However, you have to take 50 samples. 15 of these samples can be above the M value of 1000 CFU per gram, but if more than 15 are above this 100,000 CFU per gram, then there is a hygiene problem and you have to take your management actions. What is nice about this legislation also is that it is currently 15 samples, but when the criterion was first implemented, the level was 20. C value was 20, so in 2018, then in 2020 it became 15, and in 2025 it will become 10. So this is a criterion where slowly the EU is pressing, you could say, the hygiene in slaughterhouses. And already 10 years beforehand, people knew that this is coming. So it's a slow pressure towards better hygiene. People can work towards it in order to comply with these criteria. And I think this is a good example of food safety management on the more longer term, that you set a certain criteria and that you slowly push it in the right direction so that companies have the time to adapt to certain legislation, but that slowly on you improve the hygiene of your processes. A second nice thing about this legislation is that in the legislation is written that in case that your Campylobacter analysis does show that for a very long time you comply with this regulation, if then you don't have to do this every week, but you only have to do this 1 week per 2 weeks. And so that is also, it gives a reward that if you comply with the legislation for a very long time, you can reduce the frequency of sampling. Of course, it's not stopping the sampling. You have to still do it, but only with half of the effort. So again, that then costs less money, which is a good thing. So if you comply with the criterion for a very long time, you get really a reward. So this is also a nice thing, a microbiological criterion, where in the legislation, a reward is given to push companies in the right direction. One is pushing by putting more pressure, but this is by pushing by giving people a reward if they comply with the criterion for a very long time. So then the last example of a criterion is a process criterion, which is quantitative, 3 class, and the C value is equal to 0. And this is again from the Codex Code of Hygiene for Powdered Infant Formula for infants. So this is again an indicator, it's mesophiles, so it's the earlier one was Enterobacteriaceae, which are more closely related, of course, to infective pathogenic microorganisms. This is a more generic group, you could say, hygiene indicator. And here for the mesophiles, you have to take 5 samples. 2 of these samples can be between 500 and 5,000. None of the samples are allowed to be above. None of the samples are allowed to be above 5,000 per gram, and the other samples have to be below 500 CFU per gram. So this is an example of a 3-class plan that is quantitative, and the C value it does not equal to 0. So in the Netherlands, or in Europe and Germany, we have had also an outbreak of EHEC in sprouts. And in certain cases, microbiological criteria are set up after a problem did occur. We call that in Dutch, close to well after the calf has drowned. I think in English, it's said shutting the stable door after the horse has bolted. Probably in Portuguese or in Spanish, there will be also expressions like this, but I think that the meaning is clear. One thing, if a certain big outbreak occurs, what politicians are doing is they come up with a new criterion. And that is maybe not a good thing. You can better prevent things from occurring. But okay, these criteria now do exist. And in Europe, there is now a criterion for sprouted seeds, which says that salmonella should not be detected in 25 grams. For the product, 5 samples have to be taken. It's already a little bit forward-looking because the outbreak was with EHEC, and of course, if EHEC can be in such a sprouts, also salmonella can be there. So it is a broader criterion than just only focusing at the issue that was at stake, but also for sprouts. There is a criterion, of course, for EHEC with specific serotypes, and there it's also 5 samples, and the organism should not be detected in 25 grams. So again, this is a new criterion that came after an outbreak. But again, also in this criterion, some additional points are to be noted, because it is really multi-factor. It's not only this criterion for the products, but also in the regulation, it's written that you have to do preliminary testing of batches of seeds. So if you have a new batch of seed, you need to first sprout the seeds and then test the sprouts and or the irrigation water. And with testing the irrigation water, you have a much higher probability of detecting the contamination, because even a localized contamination can be much better found in the irrigation water. So this is again helping us to initially, before using a batch of seed, to detect certain deviations. So this is again helping us to prevent things beforehand from going wrong. But also here, there is a derogation for preliminary testing of the batches of seed. If you have a very good management system in place to handle your seeds so that you are more sure that the seeds are free of pathogens, and also if you have 6 months of negatives. If during 6 months you never have found positives, you don't have to test the batches of seed. So again, a two-sided adaptation of the legislation. So not only product testing, but also the seed testing, but also a derogation that you can reduce the frequency of testing if you have a good management system and if you have for a long time only negatives. So now let's look at the performance of sampling plans. The most stringent plan was salmonella with 60 samples of 25 grams. And in the legislation, in the codex documents, you can see that this sampling plan does not give zero risk. Below the sampling plan is written that this sampling plan gives a 95% confidence that a lot of food that contains on average 1 organism in 373 grams and that has a standard deviation of 0.8 would be rejected. And that means then that more than 0 out of the 60 samples would give a positive result. So this is 1 organism in 373 grams, or 0.0027 CFU per gram. And this is not zero. There is a potential that salmonella is sometimes present. So in 1 kilogram of powder, there will be potentially salmonella present. And in a ton of material, there is also a risk that the organism is present. So these performances can be determined by the ICMSF sampling plan tool. And this ICMSF sampling plan tool can be downloaded from our website. And we can determine this performance of the sampling plan for salmonella, but also for all the other organisms that I mentioned. So we have the salmonella, the Enterobacteriaceae, Listeria, Mesophilus, and Campylobacter. And you can see here the performance of these sampling plans. Here, the numbers that I explained. So you can see that fewer samples have to be taken here, except for the Campylobacter, where we take a lot of samples during the week, but the C value equals at the beginning 20 in 2018. We also see here qualitative plans with presence or absence in 25 grams or in 10 grams. And here you see quantitative limits. And you see here the performance. And we see that we accept much higher levels of Mesophilus, since that's an indicator, or of Campylobacter, because that's not that's a raw product that still has to be cooked, than, for instance, for Listeria or for Salmonella. So you can see here the performance in a graph. So the same data for Salmonella, for Enterobacteriaceae, for Listeria, for Mesophilus, and for Campylobacter. So you see the organism much more the most severe organism, especially in the powdered infant formula, going towards the Campylobacter on the raw poultry. And you can see here the probability of rejection of a batch depending on the log arithmetic mean of the number of organisms in our food products. So for Salmonella and BIF, we have a very high probability of detecting it at even very low levels of the organism, but at even these levels, for instance, for instance 10 CFU per gram for Campylobacter, almost always you will be below the criterion, and you could say, always accept such a batch. So you can see here the performance depending on the log arithmetic mean of the number of organisms, and you can see a very large deviation between the different sampling plans. And like I mentioned at the beginning, there is not one sampling plan, there are all kinds of different sampling plans, and I hope it is clear that we want to have a much more stringent sampling plan for Salmonella than we would like to have for instance, mesophiles in a batch of powdered infant formula. So how can we now make use of sampling? So we can make use of sampling to prevent the former outbreak. Of course, that should not be our goal. Still, such an outbreak does give us information and point us towards a thing which is relevant. So it's also, of course, not stupid to close the stable door, because there are maybe a little bit more horses in your stable and they can also fly away. So it's good, of course, to also make use of the former outbreak. But it's, of course, much better to make use of sampling to verify your food safety management system. So that is definitely very important use of microbiological criteria. But also these criteria are very much used to put pressure on the food production and on primary production, on the process, on the food industry, on slaughterhouses. We put pressure to push towards better hygiene. And that pushing, of course, did happen in the sprout industry, but it also happened in the slaughterhouse for broilers in Europe because of these more and more stringent criteria. It really helps to push towards better hygiene. And especially if they are made dynamic in time, that can be useful. So to conclude my presentation, microbiological sampling plans can give very valuable information for producers and also for governments. Also for the products that you buy as a company, and also for your own to follow your own processes, but also for governments, what the industries are doing in your country, but also for import and export of your food products. The microbiological criteria can be focused at safety, but also at hygiene, and also, of course, for spoilage, although I've mainly focused now on food safety. But also for spoilage, of course, you can make use of sampling plans. You can focus your sampling plans at different places in your process. It can look at the ingredients, it can look at the ingredients environment, and it can look at the end product. And what would be my advice? Look at the ingredients, look at the environment, and look at the end product. Do not focus only on the end product, but look towards all the three different domains. I've explained different types of sampling plans, so 2-class sampling plans and 3-class sampling plans, and qualitative sampling plans and quantitative sampling plans. And these sampling plans can be combined, especially with other food safety management systems, because it's the food safety management system that gives me the confidence that your process is under control, and the microbiological criteria are only to verify and to give additional confidence. So thank you for your attention, and I give the floor back to the chairperson. Bernadette.
Thank you very much, Dr. Swittering, for your presentation. The next speaker is Dr. Robert Buchanan. Dr. Buchanan was member of the ICMSF from 1991 to 2011 and is consultant since 2012. He is Professor Emeritus of Food Safety at the University of Maryland, USA. He was the first director of the university's Center for Food Safety and Security Systems. He has almost 50 years of experience teaching, conducting research in food safety, and working at the interface between science and public health policy. First in academia, then in government service in both USDA and FDA. He has extensive experience in predictive microbiology, quantitative microbial risk assessment, microbial physiology, mycotoxicology, and food safety systems. Please, Dr. Buchanan, you can start.
Thank you. And you should be able to now see my slides. And what I'd like to do this morning is build on what Marcellus talked about today and some of the concepts and principles that underlie the use of sampling plans and microbiological testing. And I'm going to be relatively quick because as soon as I'm done here with the question and answer, I have to go teach a class in food microbiology. So anyway, my goal here is to introduce some of the testing of foods in the environment against a specified criteria. And this will include both pathogens and indicator microorganisms. And I will introduce the testing against a criterion, but I'm not going to attempt to discuss how specific criteria are set. This is a highly complicated process that usually involves multiple stakeholders and involves the governments and can take years literally. Okay, however, it is important to understand that microbiological testing is an integral part of most food safety and food quality systems. It's considered part of the due diligence that is used by both the producers of foods, all the way back on the farm, manufacturers, distribution, and marketing. And it's something that is often recommended and in some cases actually required by regulatory agencies and often required by the clients of a food manufacturer. So microbiological testing is one of those paradoxes within food microbiology. It's one of the most investigated and used aspects. There's a huge amount of testing that's done on food, some by government. More importantly, most of it's done by the industry. There is a whole specialties devoted to developing new methods, etc. But it's also one of the most poorly understood aspects, and this is primarily associated with sampling and the interpretation of results and designing systems for being able to monitor and take action when necessary in a food or in a food manufacturing system. So it's important to emphasize here, as Marcel just recently introduced, that microbiological testing is a set of technologically based, statistically based tools. And you wind up having safety. Some of the different classes that we use within food microbiology is the safety of batches, the process control verification, process controlled validation. We use investigational testing, and then we also do some just general surveillance testing or sampling. Some of this is typically done by governments when they're trying to assess the capabilities of an industry. What you do need, though, is you need the right tool for the right job. And these have different requirements, and it's important to understand what the basis of these different approaches, and then how they differ, and what are the technological and statistical tools you use with them. So you've all already had an introduction to the different types of microbiological testing in terms of attributes and variable plans. I want to emphasize here that the basic concepts are the same when you're talking about plating a sample and looking for counting the microorganisms, or you're using some of the more rapid methods such as the various DNA-based technologies. They all have a built-in issue associated with sampling. So typically, what we have is the two most types of testing that are used are either within batch or lot microbiological testing, or between lot microbiological testing. And so traditional lot testing, which is integral to what a lot of manufacturers use, is to demonstrate that the safety or the quality of a single lot of food meets a criteria that is either pertinent to safety or pertinent to quality. One of the understandings here is that it assumes no prior knowledge of the food. So this is if you were going to test something at the border, typically this is what would be involved, that you would use some kind of a lot testing. As opposed to process control testing, this is where you're looking at between batches or between lots, where you're measuring the effectiveness of your food safety system or food quality system. And basically what you're using this for is as a means of verifying that the system is continuing to function as it was designed to do. And I might note this varies from within lot testing. This assumes that whoever is using this has very much detailed knowledge of both the food and the system that they're manufacturing. So again, within versus between lot testing, the purpose of within lot testing, particularly for end product testing, is to prove that a food is safe before being released into commerce. Between lot testing, also referred to often as statistical process controlled verification testing, quite a mouthful, is to verify that the process is operating within required performance parameters. This is assuming that you totally understand your system and that you've set this up so that you're able to determine that this will lead to a higher probability of problems later on, and it's a way of trying to stop the problems before they reach a critical limit. I also want to emphasize that in reality, most microbiological testing that we do with foods and within the food industry or along the whole supply chain is actually between lot testing, and that it is used to try and head off problems. Now, I do want to introduce and emphasize here is that most of what I'm taking in this lecture and the lectures that will occur subsequently are based on much of the work of the ICMSF. And this is the two critical references, I think, for anybody that's doing large amounts of testing. And it provides both the science and the application of microbiological testing of foods. So it's from my personal use, I can look over the other side of my office and see both copies of this, and it's something that's critical for any good food microbiologist that needs to understand and apply microbiological testing. Okay, so a couple more things about this. Microbiological testing is a process that is inherently probabilistic. And what you're doing is you're trying to consider the likelihood that the target microorganism is in a food sample being examined. Again, the sample then is reflective of either the batch or the process that you're looking at, so that you can make a decision that either it's not safe to release a product or not of sufficient quality, or that you should consider additional interventions in the process. It's important to understand that you can't prove absence. You can only disprove it. However, getting a lot of zeros is actually helpful because it does allow you to do two things. It allows you to determine the likelihood of contamination is below some preset level, and that the level of confidence that you can have in the negative results. And so it's again, this is you want negative values for the most part when you're doing this types of testing. So we always get a question, at least I do, about how much do I have to test before I can assume that it's not there? And so I just give you this as a simple example. If you had 1,000 servings of a food, how many would you need to test to be absolutely certain that you're adhering to a zero tolerance, that the organism of concern is not there? And this is sort of the bad news situation. You'd actually have to test every bit, every serving you would have to be tested. And then within a serving, you'd have to basically test all of the food that was being produced or represented by that million servings, which is a problem in microbiological testing since it is a destructive process, and this would mean that you have no food left to sell. So what you're doing is you're making statistical estimates on what is the likely level in the food. Okay, as you heard from Marcel, we do this by establishing sampling plans, and a sampling plan includes a lot of things that are necessary to have a fully fleshed out sampling plan. And I do want to repeat these because this is important, because often we'll try to apply what is a standard method, not also taking care of why you're doing it. So in a sampling plan, what you're trying to do is you're trying to determine and specify the sampling method, the key assumptions you're making about the contamination, the sampling locations or sets of locations, the decision criteria, and then the action to be taken when testing foods against that microbiological criteria. And some of the things that you need to specify is going to be the degree of confidence required, and that's I'm referring to here statistical confidence, the number and size of samples, the number and size of analytical units, the frequency of testing. You need to specify what is the assumed defect rate and the standard deviation of the system. And then you also have to be cognizant of what are the lower limits of your detection, the capability of looking for and actually finding the organism or organisms of question. And then it's really important here, this shouldn't stop. These are the you should also include in a sampling plan the actions to be taken if a criterion is exceeded. What should be the disposition of product? Who are the people that need to be contaminated? If the product has already been released into commerce, who do you need to notify within the government? All of these should be planned for ahead of time. So when you're dealing with microbiological testing, the utility, the effectiveness, and the cost of testing is going to be dependent on a lot of specific parameters that you have to establish. And I might note one of the main ones is the inherent cost of the analysis. And the reality is the cost of doing a routine analysis or sets of routine analysis for a lot of food or on a continuing basis. If it is too costly, why produce the food? Because it's going to cost you more to test it than it is to try and manufacture it and sell it. So that goes without saying, but that's important. Now, I've highlighted two of the criteria that are established here. One is defect rate, and one is sensitivity of the analytical method that you're using. And the rest of these are, Marcel introduced some of them, and certainly I'll be revisiting them as we go along. But I'm going to concentrate on defining and giving examples of defect rates and sensitivity. And defect rates are one of those things that is really, when you start thinking about it, it starts to demonstrate that the better you get at controlling a pathogen or some kind of quality attribute, the harder you have to work at it. And part of this represents the concept of defect rate. And I'm going to be using here in my two examples here hopefully what you will see are on this screen, a bunch of yellow dots and a bunch of green dots. And this is if you had somebody blindfolded you and you were sticking your hand into a jar and there were some green marbles that were offensive and some yellow marbles is what you want. And so it's pretty easy. And what I've done in this is to demonstrate that if I pulled out 40 of these marbles, and by the way, if you're green, yellow colorblind, you can ask me for a different scheme of colors. I find that the green, yellow, always when I give this kind of a lecture, I always have somebody, no matter what color combination that I use, the people do not see it because they're colorblind. But anyway, pulling out 40 samples out of a jar, and if there were 50% defect rate, that 50% of the marbles were green instead of the desired yellow color, then it would be pretty easy to pull it out and to you're green, yellow colorblind. You can answer. Okay. However, when you get down to 1% defect rate, that is only 1 out of 100 marbles is green. And you pull the sample, this is the most likely sample that you would get. You would get one where they were all yellow, and people would mistakenly assume that there were no defective marbles in the batch. This is the same as true. Now, the problem here is that as the defect rate gets lower, as you're getting better and better at controlling contamination, the harder it is to use this concept in order to be able to find the residual contamination levels. And so what you would see is it would go from being able to take maybe 4 samples, all of a sudden you were up in the range of maybe 400 to detect a 1% defect rate. So this is an important concept because you must never assume, based totally on not finding a target organism, that it's not there. It is now below your capability of picking a unit and then finding it. I might note here, we do have some statistical basis that we're looking at, and often we talk about homogeneous or non-homogeneous distributions. And the statistics that we use for evaluating sampling plans is based on the concept of a random distribution within a lot. If it's not random, it becomes much more complicated in terms of sampling and getting a representative sample. You have to go from, in a totally random, you could pretty much take samples from any part of the lot and it would give you the information you're looking at. If it's not random, what you would find is something like this, where in the container, the jar that you were pulling the marbles out, they were all clustered in one area. So in order to get around that, you'd have to be able to sample from multiple locations within a lot, unless you can help, you have assurances that it is randomly distributed. And when that happens, what you have to do is use different alternate sampling plans, sampling methods, which I won't go into at the time. Or what you need to do is take enough samples and then you thoroughly mix them. And this gets you back to a more normalization of the distribution as if it was random. So if you took enough samples out of here and you mixed them all together, then you'd have a possibility of detecting them. Another important point that I want to emphasize here is that microbiological contamination typically flows with the process. Wherever it was introduced, it will then follow the product down the processing steps. And typically, one would expect it to, at least some of it, to wind up in the final product. I might note conceptually, there's nothing special about an end product testing. It's basically an integration of all the steps that took place before, both in terms of sources of contamination and also interventions that get rid of the contamination. However, its true significance is that this is the point where the regulatory controls associated with food start. And this is where until you, typically in most governments, until you release it into commerce, it's not in their purview. That's up to the manufacturer to deal with this. But once it's in its final package and get ready to go into commerce, this is when the regulatory controls start. I might also note that here, this is a point where it is very important to be able to take and have some in-process controls or sampling, because it greatly simplifies if you have to go back and do a root cause. You can sample at, say, this point, and then in the end product. And this way, if you had nothing up here, but all of a sudden here, you could concentrate your activities of trying to find the problem at these sites where you start picking it up. Okay, a little bit about requirements for testing. And there are two primary factors when you're testing for anything, including microorganisms. And actually there's one. The first one is for chemical and anything. And that's basically that you have to have, in order to detect the organisms, you have to be able to get to distinguish signal over noise. And this is basics for any chemical analysis. This is the basics for anything, is being able to distinguish between just what's going on, random types of things, versus some effect that indicates that you're out of control. The other one that is unique to microorganisms or microbiological testing is the impact of the particulate nature of microorganisms. You don't have half of a microorganisms. You have microorganisms that are intact and can be treated as particles. And I might note here, this is important for both the principles for both traditional and rapid methods. You have to be able to consider the particulate nature of microorganisms. And so that's one of the things that has come out of ICMS studying the detection limits, etc., is that the key to the sensitivity of a method is going to be associated with the size of the analytical unit. It's a key determinant. And just to go through this, and we've done some calculations on this. So to be 99% confident that you would detect the presence of a specific organism, okay, you have to have at least one cell in the analytical unit. So to be confident that you had at least one cell in the analytical unit, the mean concentration is going to be dependent on the size of the analytical unit you're using. So if you're going to be sampling and then evaluating 1 ml of a sample or 1 gram of a sample, the mean log concentration to be 99% confident is 1.3 log of 1.3. If you do those, if you drop it to a tenth of a mil, it goes up to 2.3. It is if you go to 10 microliters, it's 3.3, and if you go up to go down to 1 microliter, it's going to be, you have to have at least you're in the range here of 4.3 log CFUs per mil or per gram. I might note here, this is dependent on the sigma that you assume, and it will vary. And I might note here that the ICMS tools that you can use that are available on the ICMSF website can allow you to go back and do these kinds of calculations if you need to. And it is available and it is for free to download. So I highly recommend it. I use it all the time. Okay, so here is our dilemma. In the period over the time since I first became a food microbiologist, which was ancient history, it was certainly well before Marcel was born. The standard practice was you always analyzed 1 mil. And what that did is it allows you to be fairly confident that you're getting the organism in, or at least you know you're down at this kind of a level. Since that time, with the advent of better sampling, better equipment for doing dilutions, etc., we've moved from here down to here. And now it's not unusual to see these kinds of samples, but it means that you must have a higher level of your organism in the food sample if you're going to find it. Okay, so get around this limit, you need to either increase the size of the analytical units being examined, or increase the number of analytical units being examined, or you need to either enrich the sample by enrichment culturing, or concentrate the sample by some form of concentration of the material. Could be something as simple as centrifugation, for example. But these are critical importance if you're going to be able to detect and have a high confidence in what you're doing. Okay, so what I've attempted to do in this is to just give you an introduction. And the important things to understand is that microbiological testing is a set of technologically, statistically based tools. And again, this is so that you have confidence that when you compare it against an established criterion, that you're actually measuring and evaluating you're supposed to. Two, the sensitivity and effectiveness of these tools are dependent on several factors, including the microbiological levels in the sample and a lot of the details that go into being able to evaluate an organism, all of which I didn't have time to go into great detail. And there are, numerous reference books on different methods. Okay, and I'm going to stop here and turn it back. Hello. Bernadette, I turned it over to you.
Okay. Thank you very much, Dr. Buchanan, for this very, very interesting presentation. Sorry for the delay. And I know that you have to leave. So I will ask you to answer one question that you received from the audience. When there are two limits for testing a lot of a certain food, you have the inferior limit, the little m, and the higher limit, it's a big M. Which limit should be used when only one sample is tested? It's little m or it's big M?
You're on mute, Bob. You are still on mute.
Bob, you are in mute.
Okay, if you're doing a 3-class plan, that's the only time you use a big M. The rest of it is built into your sampling plan, and there should be established that would do a single sample, a single analysis. You want to have more than one. That would be my single approach to this. I don't know, throw it over to Marcel because he may have a different opinion.
Marcel, do you want to add something?
I agree with Bob. If there is a sampling plan, it's defining an N, it's defining a small m and a big M and a C value. And you have to follow that sampling plan. And there is an N given, for instance, 5 samples. And you have to follow all the part of the sampling plan. And otherwise, you're not following the sampling plan. If you only take one sample, you do not follow the sampling plan. So I don't want to speak if you then have to follow the small m or the big M, because you're not following the sampling plan. I'm very strict in that. If you follow the sampling plan, you have to follow the ISO method or have an equal method as the ISO method. You have to follow the N, the small m, the big M, and the C value.
Okay.
Okay, and I apologize for having to jump off. I actually have to go and teach a class right now online. And so I will be back tomorrow and hope to see all of you there then tomorrow. So Bernadette,
Okay, thank you, Dr. Buchanan, for answering the question, and Marcel also, and thank you also for participating in this webinar today. I hope to see you again tomorrow for the presentation you have already mentioned.
Okay.
Thank you very much. Good teaching class. I would like to reinforce the audience that the talks will not be translated into Spanish and Portuguese. The system does not allow this. And I also would like to inform the participants that most of the talks will be available for download later. Some of the presenters have confidential data, so these ones will not be available, but you will see by the end of the webinar which talks will be available for download. Okay, we are right on time. So now we will have again Dr. Marcel Swietering talking again. Please, Marcel, you have 1 minute break if you want. The floor is yours again. Please, you have until 11:45, a little bit more, for your presentation. Thank you very much.
Okay, thank you, Bernadette. And I don't need 1 minute of break. I had half an hour of break, fortunately, because that's why we put Bob in between, because to give 2 presentations on a row, then I definitely would have had needed 1 or 2 minutes break, but I've had half an hour to get again under control. And also this lecture is about control, and it's about control measures. So in my earlier presentation, I explained about the HACCP and that we need to have validated control measures. So microbiological sampling is one part, that's for verification, but a much better solid control of your food safety system is a validated HACCP plan. However, to validate in all variable worlds is also not black and white. It also has, you could say, 50 shades of red. It is not easy to validate things in a variable world. Again, just as with sampling, we would like to have a zero risk. Again, the consumer, the management of your food company, the politicians, they want to have zero risk. But that's not possible, but we can control. But that control has a problem that there is variability and there is heterogeneity. And that's because of biology. Biology is very variable. We want to be absolutely sure, but absolute does not exist. We have food products, we have microorganisms, and we have humans. And both foods are deriving from biological material, microorganisms are biological material, and human beings are biology. And we are all different. Like we see each other, we are different. We are different human beings. We have already males and females, we have younger people, older people, we have infants, we have a difference between all kinds of people. But also there is a huge difference between microorganisms and also for raw materials or food products. Variability is also inherent in biology. In physics and in chemistry, there is also, of course, variability, but in biology, it is deliberately big because that is how you could say evolution can evolve. It's needed to have some robustness, so therefore biology is variable in order to account for all the threats that we have in our society. So variability is even for biology important, but it's also a nuisance if you want to control food safety. It's a problem. But it's not only, of course, the biology that is variable. We also have all kinds of technical parameters that show variability. My refrigerator temperature will be different than your refrigerator temperature, or maybe also the amount of time that the product is in retail for that I buy is different from the product that you buy. So also technical parameters do have their variability. So this gives us a lot of complexity, and it makes it difficult for us to make decisions. But that's where we have to live with, because this is what really is existing in our world. So this lecture is about validation, and it's important to know what validation is. We do have monitoring, and that is if, for instance, we have an HACCP plan that we have, for instance, defined a certain temperature and time of a pasteurization, then we can all the time monitor the temperature of a pasteurizer. and that we can all the time read, maybe automatically, and that we monitor that that parameter is as we have intended that that parameter should be. We can also verify that our HACCP plan is working, and that we can, for instance, do by microbiological criteria, where I and later Bob did talk about. So there we verify, we have targeted our processes that Salmonella is absent. We monitor the temperature of the pasteurizer, but then it's good to sometimes verify that if we do tests that really Salmonella is not present. So that is verification, that we afterwards look if the process is going as intended. But validation is a process we do beforehand. We obtain evidence that the control measure, if properly implemented, is capable of controlling the hazard to a specified outcome. So for instance, in validation, we define that a 72 degrees 20 seconds pasteurization gives more than a 6D reduction of Salmonella, or more than a 6D reduction of Listeria. So that we test beforehand, we validate that that process then gives a 6D reduction. Then we can monitor that really the temperature is 72 degrees by reading the thermometer, and then later on we can verify that really in 5 samples, for instance, the organism is absent. So that is validation. Validation is obtaining the evidence that the control measure is, if properly implemented, capable of controlling the hazards. So how can we do a validation? For that we can obtain experimental evidence, and that we can do by challenge testing, for instance, with lab scale testing with the pathogen on our lab bench. But in certain cases, we also want to do it in more upscaled in process, for instance. But of course, in a process, you are not going to work with pathogenic microorganisms, with Listeria or with Salmonella. So in those cases, if you go to a pilot plant level or the process levels, in many cases, you make use of indicators or surrogates. So one approach is really challenge testing with the organisms in the process line or in lab simulating conditions. There you do the experiments yourself. But you can also make use of quantitative microbiology. Quantitative microbiology is a useful tool to collect all kinds of information. But for quantitative microbiology, you always have to think about how representative is the model for my particular situation. We have to include variability, we have to include uncertainty. We can make use of all kinds of databases that we can find, and more people are making use of meta-analysis, that you collect a lot of evidence and literature and collect all that information and build your models based on all that information that you can access from the scientific literature and from databases and from all kinds of reports. So the ICMSF has developed the FSO concept. And the FSO concept sets that you have a certain food safety objective that is a level that is acceptable at the moment of consumption. This food safety objective is related to an appropriate level of protection. I will not talk about that, but let's assume that a food safety objective is set. Then we can make use of the ICMSF equation that says that if you start with an initial level, there are in the process a number of reduction stages, for instance, pasteurization or washing or inactivation processes. There can be growth of the microorganism, for instance, in your refrigerator, but there can also be recontamination. So if we have the initial level, we subtract all the reductions and we add the growth and the recontamination, then we get to a final level, and that should be lower than our food safety objective. We can use this equation throughout the whole food chain, and you can apply this equation also in the different parts of the food chain. For instance, you can use it in the food industry or in primary production, or if you have even 20 stages in your food processing chain, you can use for every part this equation. And every output of one of the partners of the food chain is the input for the next partner in the food chain. And overall, we need to control the level to the food safety objective, and we have intermediate controls, the performance objective, and we have processes that we need to have under control. For instance, the pasteurization process or the growth in the process chain. And we can set, for instance, a performance criterion, for instance, that we need for pasteurized milk a 6D reduction for Listeria or a 6D reduction for Salmonella in our food processing chain. And we can then validate that with a process of 72 degrees, for instance, 16 seconds, we get sufficient reduction of the organism. So the validation proves that with this process, you really get a 6D reduction. However, does a 6D reduction give then a safe process? No, because we need to have also all the other processes under control. If you have a primary production that is not paying any attention to hygiene, you start with too high levels, and then you can do a 6D reduction, but still it's not sufficient. If you have a good hygiene at primary production, you have your 6D reduction. If then the consumer is not storing the milk in the refrigerator, still problems might get out of hand. So we need to realize that this type of approach forces us to quantify. So that is a good thing, but also it forces us to look over the whole chain, because food safety is not one thing that we can do. It's always the weakest chain in the whole food chain that is determining our risks. And we need to work together to make all these chains as solid as possible in order to have the chain not breaking. So every part of this food chain need to be under control, including the consumer, including the primary production, but of course also the food industry that needs to have their processes under control and can validate that a certain process is giving a certain reduction. But this reduction does not give a safe food product. It only gives a safe food product if also all the other parts of the food chain are under control. So the ICMSF has also developed a procedure to include variability in this FSO concept, because of course the initial level or the reduction or the increase are not deterministic values. There is variability in these values. And we can include this variability and have a variation in the initial value, a variation in the reduction, and a variation in the increase, add them all up, and then we get to a certain FSO that is even a wider interval because it's the addition of all these variabilities. And then we can see that in this case, we have a very small probability of 0.2% that we get, in this case, over our FSO of, for instance, 2. So we can include variability also in this FSO equation in order to look at the validation of a process. And like for the sampling plan, the ICMSF has also developed a tool to make the calculations for these FSO equation, including variability. If we can assume that this variability is log normally distributed, then this tool can help you to see what the performance is of your whole processes and how often you will be over your FSO. If you have other distributions, if they are not normal, then you really have to perform a quantitative risk analysis and make use of more complicated tools. But this tool can help you if you have your FSO equation and if you want to include variability that is normally distributed. Again, this forces to look all over the food chain. It forces to quantify variables, but it also forces you to quantify variability. And that is again a good thing, because in real life there is variability. And this tool can also be freely downloaded from the website icmsf.org. What are now sources of variability? And I mentioned them already. It's the microorganism is variable, the product is variable, the process and the chain, food chain are variable, and also humans are variable. So that makes it all complicated. And we have experimental error, biological variability. We have effects of the cell history of different physiological states of cells. We have genetic variability, we have strain variability, product-specific effects, variability in all controlling factors, variability of our environment, variability of human beings. So there is a lot of variability. Again, that's a fact of life that we have to live with. And it's good to try to quantify all these sources of variability in order to get realistic predictions and to determine the sources of this variability, but also to rank their importance, because some of them are more important than others. And it's good to know which ones are the most determinant factors for variability, because those factors we want to have under control. Of course, some of these factors are not difficult to get under control, but let's determine the ones that are important and that we can control where possible. Additionally, this can also give us a lot of biological insight, which is of course interesting as biologists. So the dilemma is that for this we need data. We need lots of data of levels of microorganisms, of growth of microorganisms, of inactivation of microorganisms, of their recontamination. So it's all not that easy. So we can then do model experiments, we can make use of surrogates and plants, but then we have to select a strain, we can decide to make use of cocktails, we have to decide on what prehistory we are using for the strains that we are going to use in our model experiments or in our plants. And that is all not easy to do. But one thing that I often see in the literature is that in many cases, people pre-culture their cells at 37 degrees. And then they are going to determine it in a model experiment at, for instance, 7 degrees or 4 degrees. And this is definitely not realistic for practice, because generally the contaminants in organisms like Listeria is not coming from a hot environment and is then going to fall into a food product. In those cases, you will have often a very long lag phase that in practice you will not encounter. So it's important to make your prehistory and the strain selection to make them realistic and to apply them in a way that it can also be representative for the process that you are investigating. So now let's look at this variability. We have here the effect of the pH on the specific growth rate of Listeria monocytogenes. And this work has been done by a PhD student, Dia Ariani, and that was a very accurate lady that performed her experiments always very accurately. That's why we hired her. And this is an experimental error that she determined. So I invite you, do it better than her, and it will not be easy to do so. You see here variability. There is variability between different experimental results. This was all done by bioscreen, and you get variable results. She worked accurately, but biology is variable. But she did not only do reproductions at the same day of experiments, she also took biological replicates. So she did redo the experiment at another day, and then did it again at another day. And then you see even a larger variability in her experiments. This was for strain Scott A, but then she did it also for EGDE, another strain, and for again another strain, and again another strain, and then she did do that for 20 strains in total. You see here huge variability. So you see here a large variability in the growth rate at rather high pHs, but especially in these low pH ranges, there is a huge variability. And this has, of course, an enormous impact on the potential of growth of the organism, because, for instance, this pH, certain strains do not grow and other strains have a high growth rate. And here, at even lower pHs, that also occurs. So this is very relevant to consider. If we now make predictions with the models that she has developed, you can see here that there is a very wide interval of the growth of Listeria in, for instance, a food product with a certain pH, water activity, and temperature. As an example, the growth of Listeria in milk. So what will now be the level of Listeria after 8 days? If you have to say the level of Listeria after 8 days, there is not one value. There is a very big range. You can only say it's somewhere between 6 and 9 logs. People then can say, "What? You have a lousy model because this is not accurate." My response would be, no, this is a good model because reality is not one value. It depends on which organism is contaminating your milk. This variability you will really encounter in practice. So we cannot give one specific outcome. There is variability. She also did look at the inactivation of Listeria monocytogenes. Here you see again the experimental error that she made in doing an inactivation treatment. She then also did determine this experiment on another day with a new pre-culture, with a new prepared batch of medium. So you see then a bigger error. But apart from doing reproductions and really reproduce the experiments, she also did do it for the 20 different strains. And this strain variability is even much bigger than the reproduction error and the repetition error. So we see again a very large deviation, very large variability between different strains. We also compared these data with a meta-analysis. So already 14 years ago, a postdoc with me determined the inactivation rate for Listeria monocytogenes from all kinds of different literature sources. So she collected 940 D values from all kinds of sources for Listeria monocytogenes and also for other pathogens. But here you see the data for Listeria monocytogenes. And you see here a huge variability. You see that the D value can be a factor 10 higher or a factor 10 lower than the average value. So there is a huge variability. But these were data for all kinds of different strains of Listeria, for all kinds of different products, for all kinds of different characteristics. So this is largely variable between different labs, between different history of pre-cultures, etc., etc. So we see here a huge variability. But we can now compare with the data that DIA did obtain for the 3 different temperatures and the 20 different strains, how much the strain variation will be responsible for this variation. So what we do is we take out all the data from this graph and we only keep the lines, so the 95% prediction interval and the mean. And if we do so and we plot the 20 different strains, we can see that these 20 different strains really determine a very big part of this variability that we encountered in this study, where we did evaluate all the data from the literature that had a huge amount of variability sources. So by only having 20 different strains and for the rest have equal conditions, we can already explain a huge part of this variability. So strain variability is a very important source of variability in validation studies. I showed you this graph that for growth, there is a very big variation. And you see here that after 8 days, I cannot exactly say what the level of Listeria will be. But if I now do a process where I first have this growth and then have an inactivation, so I make use of the same graph as I have here, but I also do an inactivation process afterwards, then you can see that the effect of inactivation even is much bigger than the effect of growth. So it looks as if there is now only a very slight deviation for growth, but it's exactly the same data as you see here, but on a different scale, because we have now also sometimes huge inactivation. So certain strains are fully inactivated at 65 degrees, 1 minute, and really they have minus 15 logs reduction or 20 log reduction, while others only have 1 or 2 logs reduction. So we can see that both growth and inactivation show large variability, but inactivation shows the biggest effect. And in combining this, we did write an article about microbiological variability and saying that all variabilities are equal, but some are more equal than others. And there is always a lot of variability in growth or in pH inactivation or in temperature inactivation, but especially in temperature inactivation, that gives a huge variability, and that is you could say, the one that is more equal than the others. So what are now our data sources? We have all kinds of data sources. I did show you a meta-analysis. So we have all kinds of literature data, and that is a very useful source. We can combine all kinds of different data from the literature. Often they are already gathered in databases that we can make use of. This shows a big variation, but it's also a very quick source of collecting data. Also, as a food company or as a government, you in many cases have historical data, and this historical data is also a useful source to make use of. You can do yourself experiments in the lab. What is now the best thing to do? My advice is always make use of them all. So you can only use literature data. That's a little bit lazy, you could say. It's good to also look in the history, to add that also, and to also do some experiments yourself and make a combination of all these different data. Because it's if you only use your own experimental data, maybe it's too narrow-minded. The conditions are not broad enough, but by combining it with all kinds of other sources, you get a much richer data source. You can do storage tests, you can do challenge tests, you can make use of predicted models, you can make use of safe harbors in your process, like for instance, just say 72 degrees 20 seconds in milk pasteurization. That has proven already for 100 years that it is under control. I have no objection against that. That is a safe harbor. You can make use of basic knowledge and you can make use of logic. All these sources you can use in your validation process. And the most important source is that you have to be critical in everything that you use. So have a critical eye in what you use. Because all these different sources have their weak points and their strong points and are in certain cases really representative or maybe a little bit less representative. So make use of models, make use of databases, realize that accurate models do not exist. If people say that they have an accurate model, they are lying because reality is variable. And so if they do not include the variability, then they make it more beautiful than in reality it is. You can only say that it is a realistic model. They have to include the variability, and that variability is in many cases very large. And only if one knows well all variables, including their quantified variability, then we get our realistic ranges where we will have our exposure. But it's very important then to detect the main effects that are important for the level of your microorganism, but also the important effects for the variability in that level. In many cases, the ones that are very important for the level are also important for our variability, but in certain cases it can be that one of them is only important for the level and the other is mainly important for the variability. Both are important to investigate because the level is of course important, but also the variability. We want to reduce the variability under control if possible. Of course, in legislation, we have to set a straight line. In legislation, there should be one limit. We have one criterion, and the criterion is, for instance, 5 samples of 100 CFU per gram of Listeria monocytogenes, and that is really a line in the sand. And we have to comply with that criterion, and that is the criterion that legislation has set. And we have to follow that. On the other hand, of course, we have our scientists. And I'm a scientist. I'm explaining now to you, it is not that easy. It's not all black and white. There is variability. We have a variability in the levels of the organisms in the raw materials. We have variability in the resistance of the microorganisms. We have variability in the temperature of your refrigerator. So it is not black and white. There is a distribution describing the exposure of the microorganisms. Other scientists will even come and say, yeah, but it's not only variability, we also have uncertainty, so we can even make it more complex. Of course, this variability needs to be included in the legislation that we do make, but we should have one limit. We cannot, with legislation, say everything is variable, then we don't have legislation. We need to have a line in the sand, but of course, in setting the legislation, in setting our limits, of course, we have to include or variability, and we have to include or uncertainty. So I hope that I have explained to you that it is not easy to validate processes, because we have to validate these processes in a variable world. And for that, we need to make use of data, lots of data, both from experiments, from literature. There is a rich source of information that is already available. And of course, we can collect additional experiments. So collect data, make use of data that is already available. Then, if you have done so, dare to draw a line. So you have to finally make use of all this variability information to make a decision. And in drawing that line, of course, you need to include that there is variability in setting that line. But ultimately, we have to set that line. And it is all very complex, and I'm very sorry for that, but life is complex, and that's also the reason why we are scientists, why we are academics, that we need to give the best advices with all this complicated information. That is how it is in our life, and we could also consider it in a positive way. I always say that there is a lot of variability that gives me my job, because if it would be simple, I would not have my job. It would have already been solved. But also, I really enjoy variability in life, because if everything would be the same, every day would be the same, if every human would be the same, and if every food product would be the same, I would much less enjoy my life. I enjoy my life because it's variable. But on the other hand, it is a stone in our shoes if we want to set our lines in legislation, and if we set our lines in our production process, it's a stone in the shoe, but it's also a challenge, of course, for us to make use of all these data and all these experimentations and all these models in order to set in a wise way the criteria that we need to have to provide safe food for all. So thank you for your attention, and there's, I think, now time for additional questions.
Thank you very much, Dr. Zwittering, for your very didactic and clear presentation. This is really a complex topic, and I think you were very nice in sorting the ideas out. We have some questions from our audience for you. The first one, just 1 minute. Sorry, I forgot to share my video. Oh, as I was saying, we have some questions from the audience. The first one is from Juan Carlos Pagano from Argentina. His question is, I want to know the opinion of the expositors about the use of the mobile window concept and the continuous monitoring of the food line. So you are the father of the mobile window concept, the ICMSF concept. So Marcel, please explain.
What is it? The moving window, or?
Yes, the moving window. Yeah.
Yeah, it's not my invention. Moving windows. So what we have been explaining until now is really static criteria. So what both I in my first presentation and Bob in the second presentation was giving were stable microbiological criteria. They are really meant for legislation and, for instance, for import and export. But as a food producer, it's often good to make use of the moving window approach, that you take a lot of samples during time, and in that time, in a certain period of time, collect information and make use of that for your management. And the Campylobacter criterion that I explained in my first exposure was a good example of that, because there you have, in 1 week, you have to take 50 samples, and in the beginning, nowadays, 15 of these samples can be above 1,000. So, and then you do the next week and the next week, but you can also do that in a continuous manner, so that you have always a move, and that is what really the moving window is. So that Campylobacter criterion is coming in the right direction, but you can also have a real moving window, so that every time you have, for instance, 7 days, and in these 7 days you have to take 50 samples, and 10 of them can be positive, for instance, and then every time you look 10 days back. And this is really a moving window approach. This is the sampling plan, which I think as producer and as food company is a very useful approach to follow, because you follow it all over the time. But this is, so if you do it yourself, but on the other hand, for legislation for import and export and so on, this is a little bit more difficult, because every time a new container comes into your harbor or comes at your border, and it's not really a sequence of processes. Product can come from all kinds of places. So there it's often, you could say, more batch-wise control microbiological criteria, as we have been explaining in the first 2 presentations. So my opinion will be for legislation for import and export and so on, static criteria are better. But as a food producer, the moving window approach is a very useful approach, because at least you look at the history and you can see deviations and then take action. So that I would be very positive to use that.
Okay, thank you. We have another question. Is the use of the tool provided by CMSF in the website the most practical, or are there other tools that can be used?
Yeah, of course, the answer to the question, is it the most practical? The answer is yes, because I made it. So I'm not going to say that others are better, but that is, of course, a joke. The second part of the question was, are there also other tools that can be used? And the answer to that question is also yes. And there are other tools, and then it's, of course, not up to me to say which is the most practical to use. But another tool is a tool made by the WHO AVIO, and it's created by Greg Paoli for the WHO, and it's specifically made for microbiological criteria for powdered infant formula. But in principle, it can also be used for other products. And so that is a tool that is freely available also from the website of AVIO WHO, and it's more web-based. So in that manner, you can directly apply it. You don't have to download the program and then use it. So in that sense, it's more practical. But if you have to do 50 simulations, you are working with it for a very long time. Well, with the ICMSF tool, if you download it once and you have to do 50, and you do it much more efficiently. So it depends on the use. And there is also another tool which is called Baseline, and it's from the University of Cordoba in Spain. That is also, you could say, a competing tool, which is practical and can pragmatically be used. And so that tool also has some specific characteristics that make it sometimes better than the ICMSF tool, and I think sometimes the ICMSF tool would be better to use. So I would say the 3 tools to use is the WHO AVIO tool, then the Baseline tool, or the ICMSF tool. And you can look at your preference. What also sometimes is wise, that's at least what I often do, if I write a scientific paper, that I use my own tool, of course, and I trust my own tool, but I also mistrust it always a little bit. You always have to be critical. So I often use also the tools of the competitors, you could say, to verify that the results that I get are equal. It's, in many cases, to check these things takes only 5 minutes. I'm used to use these tools, so I take the other tool and I check, of course, not all the 50 calculations, but 2 or 3 to check that things are correct and going on as intended. So for verification, I also make use of the other tools.
Great, thank you. And I have another question for you, Marcel, from Brazil, from my friend Eduardo Tondo. He made this question long time ago, not today, but I would like to forward it to you. How to establish an alternative sampling plan with performance similar to that already established?
Yeah, so that is to relate also to the former question. In the ICMSF tool, specifically, there is made the possibility to do so. And I don't think that the other tools have that ability to do so. So you can, there are 2 columns where you can have one criterion and then have, for instance, the legal criterion. And then there's another column where you then can say, I now want to have the same performance with, for instance, another microbiological limit. But then, of course, if you have a lower microbiological limit, maybe you have to take a fewer number of samples or a larger number of samples. And there is a simulation button where you can press that automatically. It's then giving the same performance as the earlier program. So in the ICMSF tool, there is the possibility to set specific numbers and then say, I want to have a microbiological sampling plan with the same performance as the one that is, for instance, in the legislation. However, there is a very important aspect in here that in order to look at this performance, you need to know what the standard deviation is of your inhomogeneity, you could say. You need to, in order to look at this performance, you need to say, for instance, that the standard deviation of the distribution of my microbiological contamination is, for instance, 0.8, or it is 0.5, or it is 1.2. If you know that, you can include that, and then you can calculate the performance and make them exactly equal. So technically speaking, this is easy to do. The tool is made for it. However, it's very difficult to be sure what the distribution is of your contaminants, what the standard deviation of that contaminant, of the distribution of that contaminant is. Because in order to determine the average level, maybe if you take 5 samples or 10 samples, you can reasonably determine the average. But in order to really know the standard deviation, you need to have a huge amount of data. And in many cases, we do not have that big amount of data. But if you have the standard deviation, you can easily perform this task. But the issue is not the technical calculation of this, but it is in setting your standard deviation. That is the most difficult thing, because for that you need to have huge amount of data.
We thank Dr. Marcel for participating in this interesting discussion session. We will have now a 19-minute coffee break. Please come back at 11:15 Brazil time. Thank you.
Thank you.
O FORC é um centro de pessoas, que é um centro que agrega pessoas que trabalham, que desenvolvem pesquisa aplicada em diversos pontos da ciência do alimento e da nutrição.
Já se pensava em fazer um centro de alimentos dentro da USP. E a gente achava que a USP, se ela unisse todos os fragmentos, todos os grupos que trabalham com alimentos numa única coisa, nós ficaríamos invencíveis.
Por que não? Por que não fazemos esse projeto, né? E aí nós começamos a conversar e foi um longo processo, porque foram 2 anos para a FAPESP decidir que nós tínhamos expertise suficiente para ter um centro.
A ciência do alimento, a ciência da nutrição, ela é multidisciplinar por definição. Então eu costumo brincar sempre que o mundo tem 9 bilhões de especialistas em ciência de alimentos. todo mundo entende de alimentos, porque todo mundo come. Existe uma frase famosa do Luiz Fernando Veríssimo: o poder acaba, a visão acaba, o sexo acaba, mas a fome continua.
Uma das coisas que a gente realmente mostrou é que esse tema tem uma importância capital para o país. 30%, quase 40% do nosso PIB vem justamente desse setor, do setor da agricultura, do setor de alimentos. E isso daí tem um reflexo direto, nutrição, para a população.
Nós podemos, em parceria com a indústria, desenvolver projetos que sejam cientificamente de alto padrão, aplicáveis para a indústria que beneficiem a sociedade.
A pós-graduação é importantíssima porque a maior parte justamente de toda a pesquisa que é feita, ela é feita no laboratório por pós-graduandos. Quer dizer, os mestrandos e doutorandos, eles formam a maior parte, vamos dizer assim, dos nossos recursos humanos. Um recurso humano altamente especializado.
Hoje nós temos no FORC 30 jovens pesquisadores trabalhando com a gente e nós conseguimos chamar inclusive pesquisadores do exterior.
A gente percebe que existe um avanço considerável em quantidade e em qualidade também.
Uma das coisas que também a gente quer muito é que a gente tenha essa parceria com universidades e institutos de pesquisa mundiais que trabalhem com alimentos e nutrição. E isso está acontecendo de maneira bem forte.
Se vier uma indústria aqui dizendo que quer desenvolver alguma coisa, quer aprofundar um determinado tema, nós temos as competências aqui para ajudar.
Dentro de uma universidade, dentro de um laboratório, você tem a condição de trazer aquilo lá, aquela ideia, torná-la realidade. E por isso que nós somos apaixonados pelo nosso trabalho.
Eu acho que inovação é quando você vê alguma coisa de um jeito diferente do que os outros veem.
Nós criamos lá embaixo um laboratório que é de primeiríssimo mundo e a gente consegue fazer pesquisas de altíssima qualidade.
Essa é a nossa pretensão, que a gente tenha um centro de pesquisas dentro da Universidade de São Paulo que seja independente.
Consolidar o grupo e ir para frente daí. Se tornar uma referência dentro do universo de alimentos e nutrição para o país e para o mundo.
Nós queremos continuar formando gente muito boa, mas nós queremos formar gente muito boa e produzir ciência muito boa. E como é que a ciência é muito boa? A ciência do 1970 não serve mais. A ciência do 2017 hoje ela é toda integrada, ela é toda colaborativa, ela é toda multidisciplinar, ela é toda sinérgica. O nosso centro ele está no momento certo funcionando dessa forma.
Olha, aquilo que está na nossa missão, viu? Ciência para melhorar a vida.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years' experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.
O FORC é um centro de pessoas, que é um centro que agrega pessoas que trabalham, que desenvolvem pesquisa aplicada em diversos pontos da ciência do alimento e da nutrição.
Já se pensava em fazer um centro de alimentos dentro da USP. E a gente achava que a USP, se ela unisse todos os fragmentos, todos os grupos que trabalham com alimentos numa única coisa, nós ficaríamos invencíveis.
Por que não? Por que não fazemos esse projeto, né? E aí nós começamos a conversar e foi um longo processo, porque foram 2 anos para a FAPESP decidir que nós tínhamos expertise suficiente para ter um centro.
A ciência do alimento, a ciência da nutrição, ela é multidisciplinar por definição. Então eu costumo brincar sempre que o mundo tem 9 bilhões de especialistas em ciência de alimentos. Todo mundo entende de alimentos, porque todo mundo come. Existe uma frase famosa do Luiz Fernando Veríssimo: o poder acaba, a visão acaba, o sexo acaba, mas a fome continua.
Uma das coisas que a gente realmente mostrou é que esse tema tem uma importância capital para o país. 30%, quase 40% do nosso PIB vem justamente desse setor, do setor da agricultura, do setor de alimentos. E isso daí tem um reflexo direto, nutrição para a população.
Nós podemos, em parceria com a indústria, desenvolver projetos que sejam cientificamente de alto padrão, aplicáveis para a indústria que beneficia a sociedade.
A pós-graduação é importantíssima porque a maior parte justamente de toda a pesquisa que é feita, ela é feita no laboratório por pós-graduandos. Quer dizer, os mestrandos e doutorandos, eles formam a maior parte, vamos dizer assim, dos nossos recursos humanos. Um recurso humano altamente especializado.
Hoje nós temos no FORC 30 jovens pesquisadores trabalhando com a gente e nós conseguimos chamar inclusive pesquisadores do exterior.
A gente percebe que existe um avanço considerável em quantidade e em qualidade também.
Uma das coisas que também a gente quer muito é que a gente tenha essa parceria com universidades e institutos de pesquisa mundiais que trabalhem com alimentos e nutrição. E isso está acontecendo de maneira bem forte.
Se vier uma indústria aqui dizendo que quer desenvolver alguma coisa, quer aprofundar um determinado tema, nós temos as competências aqui para ajudar.
Dentro de uma universidade, dentro de um laboratório, você tem a condição de trazer aquilo lá, aquela ideia, torná-la realidade. E por isso que nós somos apaixonados pelo nosso trabalho.
Eu acho que inovação é quando você vê alguma coisa de um jeito diferente do que os outros veem.
Nós criamos lá embaixo um laboratório que é de primeiríssimo mundo e a gente consegue fazer pesquisas de altíssima qualidade.
Essa é a nossa pretensão, que a gente tenha um centro de pesquisas dentro da Universidade de São Paulo que seja independente.
Consolidar o grupo e ir para frente daí. Se tornar uma referência dentro do universo de alimentos e nutrição para o país e para o mundo.
Nós queremos continuar formando gente muito boa, mas nós queremos formar gente muito boa e produzir ciência muito boa. E como é que a ciência é muito boa? A ciência do 1970 não serve mais. A ciência do 2017 hoje ela é toda integrada, ela é toda colaborativa, ela é toda multidisciplinar, ela é toda sinérgica. O nosso centro ele está no momento certo funcionando dessa forma.
Olha, aquilo que está na nossa missão, viu? Ciência para melhorar a vida.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years' experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.
Well, our next speaker in this session is Dr. Leon Goris. Dr. Leon Goris is member of ICMSF since 2001 and is currently the secretary of the commission for the second period. He is a freelance food safety expert and consultant to public organizations on food safety management, including microbiological and chemical hazards. He held several jobs at Unilever as department head, food safety risk assessor, risk manager, and regulations expert. He is member of the GEMRA, FAO, WHO, and other international experts committees. He has part-time professorship at the University of Wageningen in the Netherlands. He's visiting professor at China Agricultural University, Shanghai Ocean University, and University of Shanghai for Science and Technology in China. Please, Dr. Goris, you can start your presentation.
Thank you very much, Bernadette. So in this presentation, I would like to look at the contribution of indicator organisms as a specific category of microorganisms that we can look at to see whether our food safety assurance systems work as they were designed. I will go over a number of topics in this presentation, helping also to inform you of what you can find in microorganisms in food, Book 8. And an important aspect of that we haven't touched on in the earlier presentations is the ICMSF 15 cases framework to look at what useful testing you could do in food safety assurance. And we'll go through a description of two groups of organisms, the utility organisms, the indicator organisms, but also and see how they are useful for food safety assurance, but also we will look at briefly at some of the limitations of these kinds of tests, things that we need to keep in mind when we design indicator tests. And I'll give a few examples from Book 8 on useful indicator organism tests for commodities. But also in trend analysis, indicator organisms can have particular use, so I would like to share a few slides on that as well. So food safety assurance, in this we come back to the graphic that Marcel showed. So we have a food safety system that is combining a number of activities, good practices, a specific control through HACCP. We have to make sure we understand which points where we need to control the process and make sure that those control activities are validated. We have maybe limits that we want to be within for those control points, and overall to assess whether our food safety system is working as it has been designed. We would use some microbiological testing in the form of microcriteria or environmental sampling. And the whole construction works and is almost as solid as your Maya temples in Latin America. So microcriteria have a certain place, microbiological testing has a certain place, and it is an important place. Maybe as Bob said, we think in this case, if we use microbiological testing, we think statistically. We're not sampling all the products, we're taking a subsample, but from that subsample we get information whether our ingredients are suitable for a certain food product manufacturing operation, whether our end product is suitable for consumers. And in ICMSF, we have set up a framework to look at what useful testing we would advise for different situations, different commodities, but also looking at the use of different categories of microorganisms. And you see the different microorganisms on this slide. We look at utility and indicator organisms. Those are not pathogens. People are not getting ill because of them. Some of them occur naturally on ingredients like utility organisms. They could be present on vegetable products. They could be there as the total count we measure or the total viable count we measure, yeasts and molds. And then there are indicator organisms. That's a category of organisms that are associated a little bit more to hygiene and to process control than they are to natural contamination and presence, potentially spoilage. That is more prominent with the utility organisms. And in indicator organisms, we typically look at coliforms, generic E. coli, or Enterobacteriaceae. And then we have three categories, three classes of pathogens, which I will not go into in this presentation, but also there, from moderate to serious to severe hazards, you have a kind of an increase in the risk to consumers. So we have this categories of 5 microorganisms that we built into a risk categorization framework. And we relate the consumer risk or the risk for losing process control to what happens with the microorganism that we look at, or the group of microorganisms that we look at, after the point where we apply a microbiological criterion where we do the microbiological testing. And there are three situations that we call here ABC, and going down from the impact of on the consumer from utility organisms to severe pathogens, that is where the risk increases, and going from A, B to C, also the risk increases. And let me just explain what ABC is in the next slide. But overall, you can imagine that ultimately the highest risk is the combination of C and 5 in category terms. So in this case, we have 15 conditions, 15 situations that we call case 1 to case 15. And if you look at the ABC, so what is the change in the level of the microorganism before consumption, after the testing? So either the organism can reduce in level, there's maybe no change in level, or there's an increase in level. And of course, then if there's an increase, the risk to the consumer may increase, or the risk for having a problem increases. We apply these 15 cases to have a relative test of whether food batches are acceptable, whether foods can be used, ingredients can be used for their purpose, or whether end products are acceptable to put on the market. It's what Bob called before the within lot testing. And you see that in these cases, we have cases 1 to 6 for utility and indicator organisms, and cases 7 to 15, where the highest risk is, for the pathogens of different severity levels. What we also do in our framework is to look at the distribution of microorganisms in food batches. And these microorganisms are not homogeneously distributed. There are differences in the levels of microorganisms that you sample typically in food products. Maybe you find very few microorganisms. If you take samples, maybe you find very high levels if you take a sample, if you analyze a unit. On average, you will find a number that is somewhere between the low and the high number. And with the line, the curved line, we illustrate where the average number of organisms is, and what then the relative proportion of findings of this number is in the overall lot. So you can imagine that when we have lots with high numbers, the log count will be high, and the average will be low when we have lots where we have only very few cells if we sample the batch. And we can describe those two features, so to speak, with the quantification of the mean log count. So if we have a distribution through a batch, the mean log count will be a certain number. Next to that, we can look at the standard deviation. So what is the distribution, the difference, the width of that distribution typically in a batch? And Marcel mentioned that in one of his presentations earlier today. 0.8 could be a standard deviation that describes a typical food lot that is somewhat structured, where there is more heterogeneous distribution of microorganisms. If you would have a standard deviation of 0.2, you would have a very narrow distribution, a very narrow curve, and then the counts are more close together. And in a way, you have a more homogeneous lot. So in the 15 cases example, and that has also been mentioned before, we use different sampling plant types to get across the proportionality of testing versus the risk to consumers. We use 3-class sampling plants or 2-class sampling plants. And 3-class sampling plants are typically used for utility and indicator organisms and for the moderate pathogens. And the 2-class sampling plants are typically used for the serious and the severe pathogens. So in 3-class sampling plants, you have N for the number of sample units. Small m indicates the microbiological limit for good quality. And big M indicates the limit for unacceptability. So if there's one sample over big M, a batch would not be accepted, but there could be a number of samples between small and big M where the batch could be accepted. It's marginally acceptable, but actions should be taken to see whether things are not getting out of control in following batches. Two-class sampling is more black and white, as Marcel termed it earlier. We have only one limit, and that's the small m. And if you're over the limit for a number of samples, then the batch is called defective. And if you're below the small m, then the batch is acceptable to put on the market. And with these two types, we can build up the 15 cases risk-based framework by varying the number of samples we take and by varying the number of samples we accept to be within, let's say, the small m and the big M, C, or the number of samples we would allow to be over the small m. But in the current graphic, you see how the generic advice of ICMSF is positioned for the risk-based framework. So if you go from case 1 to case 13, you see that there are many more samples taken, and there are fewer samples to be that can be over the limit or between the big M and the small m, or over the small m. And if you go from case 13 to case 15, for instance, you see that there are more samples taken again, really in an effort to make sure that the microorganisms, the distribution of microorganisms in the batch is increasingly low, so that where the risk is highest, the number of microorganisms potentially present is lowest. And you could compare it to this graph where you have a cliff edge that signals a danger zone. So you want to be away from the danger zone. So if you would take one sample, you're pretty close to the danger zone. But if you take more samples, maybe 3 or 10 samples, you are more confident that the batches that are compliant will have a lower number of microorganisms present. And if you are aware of how the distribution runs, how broad or narrow the distribution is, you can get more confidence out of the testing in terms of how you control your operation, how safe and acceptable your batches are. But now back to the utility and indicator organisms that are on top, say the top two categories, the first two categories in our framework. So as I mentioned before, the utility organisms are really organisms that are signaling general contamination. They may be present on part of the ingredients, maybe vegetable products would carry Enterobacteriaceae or other microorganisms. The total count often is high with vegetables. They may indicate also spoilage organisms or other organisms related to shelf life reductions. They certainly don't indicate safety. They do indicate maybe some other aspects, maybe quality aspects, but certainly not safety in their own right. Examples of these tests would be direct microscopical count, aerobic colony counts, or total viable counts, yeast and molds, pseudomonads, for instance, in the aerobically stored meats, or lactobacilli in mayonnaise, so where you look at some of the spoilage features. And it is important, of course, that if you think you can use a utility test to assess the suitability of your food ingredient or the proper running of your operation, that the test group of organisms or the test organism is relevant to your food. Fermented foods typically would have high aerobic colony counts, so a high aerobic colony count for those products may not say much about the status of the product, unless, for instance, you would have a pasteurized product that typically had a high ACC level like a vegetable, and then after pasteurization you would expect a low ACC count. And if you don't see a low ACC count but a relatively high aerobic colony count, you can say that maybe the process wasn't running as it was designed. Indicator organisms often are used because there is a sense of relationship with pathogens, but they are a very good, let's say, indicator of general hygiene aspects, of control of the environment, control of particular processes or cleaning activities. And like also the utility organisms, they can signal a out of control situation, maybe a process that wasn't running as designed, maybe an ingredient that was not pre-prepared as it was designed. Again, it's not necessarily indicating unsafety if a indicator organism test would be used and fails the criteria, because it's not directly related to pathogens. But if there is an out of control situation, obviously you need to take some action to investigate whether this out of control situation may have led to a pathogens being present, being surviving at undue numbers. And examples of indicator tests would be generic E. coli or coliforms, Enterobacter, maybe Listeria as a genus rather than Listeria monocytogenes, sulfate-reducing Clostridia indicating possibly maybe also opportunities for C. botulinum to be present and establish itself. And here again, also the indicator test should be very relevant for the purpose that it is going to be used for. Of course, with every test, you would want to validate that an indicator is really meaningful for a certain operation, so that when the conditions are not such as they would be in a normal operation, that it acts as a flag that there's something potentially wrong, and so that action can be taken in a timely way. And an example of this, for instance, would be that one could use in a powdered infant formula manufacturing operation, where you're very sensitive for the potential presence of Salmonella or Chronobacter organisms, that Enterobacter are followed, especially after wet cleaning, to see whether maybe there are conditions in the operation that would be conducive to the survival of Salmonella and Chronobacter. But in itself, the Enterobacter are then the flag for general hygiene. There is opportunity, and if there are low numbers, maybe there's not much opportunity for pathogens, but it's not necessarily a kind of a direct flag for the pathogens, but it's a very useful indicator. So in terms of limitations of indicator tests, as I mentioned, ideally there is a direct relationship between a pathogen and an indicator organism. That is maybe even a validated relationship, but that doesn't often happen. We don't have many examples of these. There is not much scientific evidence and certainly validation for that kind of a direct evidence. There are more examples where there's indirect evidence that when Enterobacter can survive, that also could be then situations where pathogens survive that are related in terms of their growth opportunities, their survival mechanisms. So, and that also points to bullet number 2 here. Between groups of microorganisms and individual pathogens, there are sometimes quite big differences between the ability to be present, the natural, the biological ability to be present, to grow, to survive certain mitigations. So that means that the relationship between pathogen and indicators, even if it's sometimes there, it may not be universal. It may not be always the same. It's very much influenced by product and process. So the use of indicator test needs to be really well matched to an operation and validated. Still, it could be a useful indicator as long as we know that the conditions that it indicates, normal versus out of control, would be conditions where you would be concerned about a pathogen. And then the indicator organism could be a nice way, a good way to quickly find whether a red flag has to go up and such action has to be taken. I would like to quickly give you a few examples of some useful indicator tests that we have described in Book 8, where we look at all the different commodities and look at the useful testing across different commodities. And in the book, we go phase by phase through the manufacturing operation from production to end product. And we look at what useful testing for different commodities would you have at these different stages. This is a very busy picture. It may be too small font to look and really see the words clearly, but it's just an overview that shows that if we go through book 8 and go through the different commodities, where we use utility and indicator testing is really mostly for verifying control of operation, verifying control at primary production, at ingredient stage, at environment, in process, and end product. So it's not for, let's say, validating or verifying safety. It's really, are we in control of our operation? Are we in control of the ingredients, the process, the things we do? Ultimately, that will have its bearing on the end product. So now let's look at dry milk powder and different stages in dry milk powder production. Here we have an example how it is also shared in book 8. So we look at the application area, process environment, in process testing or end product. And we have an indication of how important from the ICMSF point of view we think certain testing would be. So you see a lot of highs and one low for salmonella. So in our recommendations, we would, for dry milk powder, consider Enterobacteriaceae, a very important group to look at hygiene aspects of the environment, of the in-process production of the product as it moves to become the end product. And if you have the end product, we would think, yes, Enterobacteriaceae could still be useful as an indicator of how the hygiene had been controlled in the environment and in process. But aerobic colony count could be another useful indicator, a utility organism that is an indicator of overall process control. What you also see is that we consider salmonella testing higher in the environment and in process than in the end product. And the reason is that if you would have an operation in which the presence of salmonella in the end product is critical, depending on the use of that product. If it's not an ingredient but an end product, for instance, that is eaten without further processing, then salmonella shouldn't be present in the end product. And then it's almost more important to understand whether it is present in your operation and in your come in contact with the food as it is progressing through the production than it is to find it in the final product. You can control it best in the operation. You can't control it, and you can even not find it very well in the end product. So for control of the operation, salmonella testing, not as a criterion, but to sample from the environment, from the end process, is a very important kind of management activity. If we then go to some indicators that are useful for end product checking, we have an example here of fresh cut vegetables and frozen blanched vegetables. Fresh cut vegetables obviously have high counts of aerobic colony count, may have high counts of Enterobacteriaceae. So you couldn't use those as indicators very well for fresh cut vegetables. You can use those very well for frozen blanched vegetables, because you would expect that the blanching would reduce the aerobic colony count or Enterobacteriaceae count from the normal level quite a bit. And then if you look at what would be present on properly blanched vegetables, you could set criteria for that situation. And next to that, you could use generic E. coli as an indicator of hygiene, maybe a little bit more related to things that can go wrong in the handling or in the irrigation or otherwise handling of the vegetables, whether they're frozen and blanched or fresh. And the last example is looking across different foods and then what useful indicators could be there. In this example, we look at cooked meat, dry milk powder we saw before, and water for processing. So for cooked meat and dry milk powder, aerobic colony counts could be useful to indicate overall control of process, but for hygiene indication or for specific indication of concerns with hygiene or handling, generic E. coli and Staph aureus would be relevant for cooked meat. Enterobacteriaceae would be more relevant for dry milk powder, and yet another group, the coliforms, would be most relevant for water for processing, as for instance the coliforms relate to potential fecal contamination. So it's a way of matching the typical, also the right utility or indicator organism with the food commodity, such that it's a relevant indicator or a relevant cause for a red flag. And I would like to close the presentation with looking also at another area where we can use indicator and utility organisms for trend analysis. And the reason is that for utility organisms and indicator organisms, we use quantitative tests. We really enumerate the number of organisms in lots. And if we do that for lots in a row, if we are looking lot by lot, going at the, let's say, across lot analysis, we can get more information out of quantitative data often than just looking at presence-absence testing, for instance, for pathogens. And one example is given here. So on the left, we have a presence-absence test over 20 lots, and in one lot, there was a positive that makes this lot not accepted. But if you only see the positive every now and then, you don't know what the reason for that one positive is. You also don't know where the other ones were very close to become positive or not. And there could be many reasons for a positive to appear. Maybe it was something wrong with the ingredient, something wrong with the processing, maybe different factors coming together, making a positive just happen. But if you would use quantitative data of, let's say, based on utility organisms or indicator organisms, for instance, you could build up a record that tells you, like shown in the right panel, that your operation generally is in control, but maybe every now and then you're over the limit that you set. And then you at least have confidence that this may not be a kind of a chance event that you don't know anything about, but you can maybe look again at your operation and make it more consistent so that you know it will more robustly be below your limit, and the limit in this case in these graphics is indicated by the red dotted line. And we have a few more examples here with again the red dotted line giving a limit, different situations where we are comparing native data. We've seen the top left one, that was the last example. But if you, for instance, have the trend that is shown in the top right panel, you can see that gradually there's something building up. There's a progress towards the red line, and that means that there is something wrong in the operation, something wrong with the hygiene, or something maybe not right with the sanitation, something building up, and at some point you will go over the limit. But if you see this trend happen, you can, let's say, intervene at the right time to keep your lots performing below the red line. The lot bottom left is a lot where you see a lot of variation between different sample outcomes. So that is an operation that's very, very variable, and you want to get it much more narrow. So maybe you can do some work to get it to a much more narrow line like the one above. And then the last example to the right is that where you have a normal, well-performing operation, at some point you see an excursion over the red line, and there maybe have been a change in the operation, a change of supplier, and other causes could be there, but at least you can signal something is going out of control, and you can then intervene in a timely way. So my last slide, quickly to sum up. So I believe in food safety assurance, indicator tests, utility tests have a very important place. They are important tools for verifying environmental and process control and hygiene. They can give you good information that helps you to take the right action at the right time. And sometimes they can be coupled with pathogen testing especially when you have an out of control situation that is then relevant to consider further with pathogen testing. It can be used in many food operations, but of course you have to validate your test according to the production, the location, history, and many other factors. And there's also good value in using these tests for trend analysis, but important to say is that they don't indicate safety or unsafety of batches. So they're really illustrating and giving you a record of whether your batches are suitable, are, let's say, prepared as designed. So thank you very much for your attention.
Thank you very much, Dr. Goris, for your presentation. The last speaker of our webinar today is Dr. John Donaghy. Dr. John Donaghy is member of ICMSF since 2015. He is head of food safety at corporate quality Nestlé Switzerland, and his current responsibilities include global operational aspects of food safety microbiology, hygienes, allergens, and other prerequisite programs across factories and multiple food categories. He worked for many years as project leader in food safety microbiology at Agri-Food and Bioscience Institute, Ireland. Please, Dr. Donaghy, you can start.
Okay, thank you very much, Miguel, for the introduction, and good afternoon, everyone. Hopefully, everyone can see my slides. So I take it as silence is yes, so that's good. So as I say, I will build upon some of the speakers from earlier on today. For example, Marcel, Leon, and Bob Buchanan. You talked a lot about microbiological criteria and sampling plans, and Marcel in particular mentioned about analytical testing against microbiological criteria is just a verification method. It doesn't necessarily assure food safety. And today I'm going to talk about another verification activity, and that is verification of environmental control and the role it actually plays in helping to assure food safety microbiology in a food safety plan. And I think Leon has shown the pyramid that Marcel has shown, and this verification of environmental control really sits at the heart of that pyramid as well in terms of verifying your prerequisite programs.
John, I can't see your slides.
I have shared my screen. We try this.
Now it's coming.
Okay. Let me know, is Leona okay? Everyone can see it?
Good for me.
Okay.
Thank you.
Sure. Okay. So I will not repeat what I said before, but I will, my pointer. Okay. So we move to where is the information around verification of environmental control reside within the ICMSF books. It was first alluded to in chapter 12 of book 7, and more recently in book 8, this has actually been described in a lot of detail within chapter 4 of book 8. So really any further information about the concepts of verification of environmental control, if you want more information, you go to chapter 4 of book 8. Now, when we talk about environmental verification of environmental control, often across industries there is different terminologies used, but probably the most common terminology that is used is environmental monitoring. So we hear a lot about EMP, environmental monitoring programs, and that's the terminology that a lot of industry and governments use. In Nestlé, for example, we use the term pathogen and hygiene monitoring program. Other industries use pathogen monitoring program, but in essence, it is exactly the same thing. It is a verification of your environmental control with respect to the microbial hygiene, let's say, of your factory. So it is verification that you have the hygiene under control in your factory. And what I intend to do in this presentation is talk firstly a little bit about the importance of environmental monitoring program, and then I want to take you through some of the practical aspects of implementing an environmental monitoring program in an industrial food manufacturing setting. So why is it important? And I'll go through each of these in a little bit more detail, but just briefly, as Marcel has alluded to, product testing alone has limitations, and Bob mentioned this as well. Unless you want to test all of your product and have no product left for sale, then testing is not a way to assure food safety. Testing a finished product against criteria. It's an important element in verifying the hygiene, the good manufacturing practice, and adherence to your prerequisite programs. Also, it's important in identifying process cross-contamination, because quite often you will see that contamination by pathogens and even deviation hygiene indicators occur post the CCP, the critical control point in your factory. And finally, I always stress this point, it enables factories to take actions in response to findings, i.e. your environmental monitoring program should act as an early warning system that you know that there is something happening, that there is a deviation occurring within your factory. Sometimes people will say, this is a burden, environmental monitoring is a burden, and it's very difficult, and I have to take a lot of samples, it costs a lot of money. There's a nice recent article written by Jeffrey Kornicki, who is actually a sort of a prominent food safety industrial microbiologist in Food Safety magazine. And in this, he really talks about how environmental monitoring program can actually add to the bottom line. By a good environmental monitoring program can, in the long term, save you a lot from an economic perspective. So I want to take you through each of these points individually. And this was mentioned briefly, I think, by Bob previously. Testing microbiological testing of your finished product really has certain limitations. And if you just take the example on the left-hand side, and Bob mentioned about a defect rate, even if you have a defect rate of 0.1%, for example, even if you take 60 samples, the probability of detecting that deviation or that defect is less than 10%. So really, when we know N equals 60 is only really applied for powdered infant formula category. So by taking even less samples, you have a less chance of detecting a deviation by finished product testing. And we know, and this was alluded to by Marcel and by Bob, we know that generally with the contamination of product, it generally occurs very heterogeneously and also is at a very low level. So really trying to detect that through finished product testing is like looking for the needle in the haystack, as they say. And that's why it's important to have a good environmental monitoring plan. Secondly, a key thing for your environmental monitoring plan is that it helps to verify that your hygiene is under control, that your GMPs are working properly, and that your prerequisite programs are working properly. For example, some of the prerequisite programs which we want to verify is the hygiene of my equipment, my line design, okay, that it doesn't lead to growth areas or harboring spots in my factory? Is my zoning okay? Zoning in terms of movement of people, in terms of movement of goods, etc. If people are going in and out of production, you're not adhering to proper uniform usage in terms of cleaning of shoes, etc. Then this can actually pose a microbiological risk. Effective cleaning and sanitation, again, if that is not done properly, if we haven't got properly validated cleaning process in place, we aren't verifying our cleaning, etc., then this can lead to micro issues. And this is what our environmental monitoring plan should be able to detect. But remember, and I always stress the point that environmental monitoring program is not verification of your cleaning. We have separate verification activities for cleaning. If you've got a validated cleaning process, be it dry cleaning, wet cleaning, or controlled wet cleaning, you will have verification activities for that cleaning alone. Environmental monitoring program is over and above that, and it takes account of all other prerequisite programs as well. For example, also including your supplier management. If you're bringing in raw material from an untrusted supplier, for example, which shouldn't happen, or you have a deviation in your raw material, you want to be able to detect that if it comes into your factory and appears to grow or becomes dominant or persistent in your lines. And again, you want to make sure that your personnel are trained, they're covering all the prerequisites with respect to personal hygiene, with respect to how they clean, how they behave, how they move around the factory sector. So the environmental monitoring program is really, really essential in terms of a verification activity for these. Thirdly, your environmental monitoring program should also help to indicate process or post-process or persistence in cross-contamination. If you look, for example, through the chapter 12 in the book 7, you will see lists and lists of examples of foodborne outbreaks and foodborne cases that have resulted from cross-contamination in a factory or processing environment. So really, you have to use your environmental monitoring program to be able to detect where you could have post-process contamination. For example, this is after your CCP. And now we see even more and more with the advent of whole genome sequencing, we're now seeing persistence, being showing, real strong evidence to say that some pathogens persist in factories for a long time. If I look, Maltomil was an old example using different pulse field gel electrophoresis, but we see now using whole genome sequencing, many of the instances that are investigated through whole genome sequencing point towards a persistent pathogen, be it Salmonella, Listeria monocytogenes, in process environments. Your environmental monitoring program should be able to pick up that, and it should, in fact, I would nearly advise it should be used in conjunction with a good typing method for your pathogens. So if you introduce environmental monitoring program, if you regularly see some pathogens popping up, it is a good idea to whole genome sequence these to see if, for example, they are persistent in your factory environment. Finally, and this is what I stress as well, is your environmental monitoring or your verification of environmental control, you should act as an early warning. It should enable you to take actions a lot quicker than just doing, for example, finished product testing. If you're doing finished product testing, for example, and your test takes 2 days, 3 days, even with rapid methods, for example, your product may be on the shelves. And if you have a finding of a pathogen, it is a recall scenario. So your environmental monitoring program, if done properly, you will be able to help to alert you earlier to a deviation in microbiological hygiene within your environment. So immediately you can actually take some actions. And those actions may be that you immediately resort to a higher or an increased sampling plan, increased testing of the environment, increased testing of your product, for example. It may also help to identify what is the cause of your microhygiene. For example, do I have a water ingress, a leak? Do I have an abnormal condensation? Have I dismantled some equipment that somehow led to contamination of the environment? And it allows you, most importantly, is to do your corrections and your corrective actions for long term so that you don't get a repeat. And if it really is a serious situation, that, for example, you have a finding of a pathogen in a product contact surface, for example, it allows you to stop the line immediately, without continuing to produce with a pathogen end up in your finished product. So all of these, and this last point is really, an important point for me, is this early warning aspect. And I always say environmental monitoring should be a hunting exercise. There should be no prizes for finding nothing. In fact, it should be prizes for finding something. You should look as hard as you can to make sure that you've looked in all the difficult to reach places and to see if you can find anything. And it should act as an early warning so that you can react and do the corrections. And it is not meant there for compliance. It is very much a verification that your environment is under control from a hygiene perspective. So now that hopefully I've convinced you that environmental monitoring or verification of environmental control is important, I want to go through some of the sort of practicalities of actually setting up a plan. So of course, and I'll go through these again in detail as well, it's always about the where to sample, the what organisms to sample, the how often do I need it in terms of the frequency, and also the how in terms of what tools do I need to use practically to sample with, but also what tools do I need to use in terms of being able to spot trends, to be able to see my data quickly. Quite often we see that people have reasonable environmental monitoring plans, but it's stored in an Excel, it's stored in in some format that's not easily to digest, it's not easy to establish trends from, etc. and it becomes a little bit of a reactive tool. Just, we should have a good system to be able to trend and track and respond. So if I take in terms of the where to sample, most environmental monitoring programs are built around a zoning concept. That is, you have your factory zoned in such a way that you know where your high risk areas are, we call zone 1. The lesser risk area is zone 2, the still lesser areas are zone 3, and then zone 4. Zone 1 tends to be those product contact surfaces, and these would be your areas that you would actually, you are, let's say, more vulnerable to contaminating your finished product. Then your zone 2 would be probably parts of that equipment that could potentially impact your product contact surface. And then you go right out to zone 4, which tends to be further away and maybe even outside your production area. If I look at this, so everyone will call this a slightly different name across different industries, but it tends to be based on this zoning risk assessment concept. If I look at the arrow on the left-hand side of the screen, is what we do typically in Nestle. Our zone 1 samples are what we call line samples. So this will be residues on our line, and then our zone 2 will be E1, and then zone 3 will be E2, environment 2. E3 is further away, let's say lower risk areas. So this is sort of the concept that should be applied when you're setting up your environmental monitoring program. Trying to identify what are these areas. Sometimes there's a lot of discussion points about what's a zone 2, what's a zone 3, but it is important that you try to differentiate these different zones in your production area. Also, in terms of where to sample, it is also very important, and I come back a little bit to the trending aspects, is to map out either on your CAD drawing or your factory drawings, to map out where you actually take the samples. So that you know, in this example here, you see on the left-hand side, where's my green areas, where's my red areas, where's my zone 1 samples, where's my zone 2, zone 3, zone 4, etc. And depending on what system people have, they may have a database, they may have SAP, they may have just an Excel, but to write actually good metadata associated with your sampling point. You go back in 6 months' time, you have an issue, and you go back and look at your data and say, where did I take this sample from? I can say it was the oven door, it was the exit from the freezer number 1 or freezer number 2. So be descriptive with where you are taking your sampling points, and actually overlay your sampling points on a CAD drawing of the factory. Because when you try, and I'll show you later some of the new digital tools that are available, when you want to track and trace this to respond or to investigate, this is extremely important that you have good data at where you've taken your samples from. So here are just some examples, let's say, of what we would consider our zone 1 or our line samples. Top left-hand corner, pizza line. So you'd be taking, for example, some dough residues, for example, from the pizza base. You'd take as your line samples. You see them on the filler on the left-hand side for ice cream. You see on the right-hand side, chocolate, for example, you would see the points where you would actually take your samples. So this is actually not finished product, packaged finished product, but this is product that is really on your line, on your product contact surface. And the other thing which sometimes people forget is actually your cleaning tools themselves. Remember, if you're doing dry cleaning in a factory and you use something like this, like a scoop and a brush, you are brushing, for example, your product contact surface. So it's also a good idea to include your cleaning tools actually within your sampling plan. Some examples of zone 2. So now we're moving a bit further away from let's say the high risk area, further away from the product contact surface. So again, here on the left, you see this is in a chilled culinary factory. So you're taking samples from the edge of tote bins or whatever that you are actually carrying your material with. You see on the right-hand side, top right-hand side, you see where the swabbing has been taken. It's further away from the contact surface. It's further away from the belt of the machine, but yet it could possibly contaminate that belt at some stage, and the belt could contaminate the finished product. Also, vacuum cleaners. Again, we talk about cleaning tools. A lot of industries will use these large industrial vacuums to take samples. An important point here is if you are taking samples, you make sure that you're not overlapping your samples, because then it's very difficult to trace. Quite often, you'll take your sample from the vacuum bag, so that will be your sample. But if you have actually used that vacuum to sample your line, to sample the edges of the machine, and to sample the floor, then I have a combination of an E1, of a zone 1, a zone 2, and a zone 3. So you have to be very careful if you're using tools like vacuum cleaners, is that you have either segregate or differentiate the vacuum cleaners from one zone to the other. So this is an important, because otherwise, if you find a positive in your vacuum cleaner and you've used different areas, you will not know where it's come from. So in terms of your investigation, it's going to be extremely difficult. And then when we move to, let's say, the zone 3 and zone 4, here we're getting further away. Generally, you're maybe on the edges of your production facility, or maybe even outside your production facilities. You could be drain samples, you could be forklift wheels of a forklift truck, or it could be somewhere in a warehouse. And this tends to be, what do I have there that actually could put pressure on my next sample that's closer to production, or closer to the zone 2, or closer even to zone 1. So you will find that what we would typically do, we're not taking a large number of samples in these areas as part of our environmental monitoring program, but for example, as part of an investigation, for example, we would then go and see, well, if I have a finding in my zone 2 or zone 1, I might just say, well, where could that have come from? Could someone have crossed a zoning boundary with their forklift truck? And could my salmonella or a listeria or high EBs have come in on the wheels of the forklift truck? So we tend to not do routinely high numbers of samples in these outer areas, but they will be very much included as part of an investigation. So then the next question is, what microorganisms do I sample for? And I always try to say that we try to split between dry factories and wet factories. And so the top one is my dry factory. This will be, for example, milk powder, confectionery, dry culinary. My bottom factory, wet factory, may be ice cream, chilled, frozen culinary, etc. So that almost dictates the organisms that you will actually start to look for, and also the nature of the cleaning you're doing as well. Typically in a dry factory, you will have a lot of dry cleaning processes. This is where you do not use any water for your cleaning. You'll just do dry cleaning. Then you go the other extreme of wet, is where you'll be foaming, you'll be spraying, you'll be using a lot of water. So that dictates also the organisms that you should look for. And generally for the dry environments, the pathogens of choice will be salmonella primarily. And if it's powdered infant formula, you will also use or a test for Chronobacter in your environmental samples. If I am in a wet factory, for example, chilled and frozen factories, my pathogen of choice will be Listeria monocytogenes. And then, as Leon has just indicated on hygiene indicators, generally for the dry factories, it will be primarily EB, Enterobacteriaceae. And in the chilled and frozen factories or wet factories, the indicator will be Listeria species, generic Listeria. Sometimes these, for example, in the EB, depending also on the area, the country that you're in, the finished product legislation may be coliforms, for example, and in some cases people use coliforms as their hygiene indicator in dry factories, because simply that's also what is in the legislation and to be consistent. So we don't within Nestle, it's not hard and fast, but we definitely advise you have to have an appropriate hygiene indicator alongside an appropriate pathogen for the appropriate factory or the appropriate environment. We may also include some other organism. For example, you may be part of your environmental monitoring program, or you may have Bacillus cereus, depending on the nature of the product, or if that organism may pose a risk, of a deviation in your finished product specification. But in general, as a rule of thumb, the organisms on the screen is what we go after in the dry and wet factories. Then in terms of setting up your plan, we have two aspects. One is the routine, and I call that the routine is your normal sampling plan. So you decide what organism am I going to do, I select my sampling points in factories, and I decide how often I'm going to do them. and that's your routine. Then you have on the other side is your investigative. This is over and above and supplements your routine sampling plan. And just to go through typically what a routine sampling plan may look like, if I take, again, going back to my zones, and this is just for illustrative purposes, what I might have is I would pick a number of sampling sites in my zone 1, say I pick 20 sites, and I will decide that I sample each of those sites once per week. In zone 2, I might pick a similar or less number of sampling sites, and I might decide I will test those every 2 weeks, so 2 times a month. And then zone 3, I will pick a number of sites, and I will decide to maybe only do those once per month. Zone 4, I will take less samples and I will test them less frequently. So you see, overall, you end up, and what we aim for within Nestle in particular, what we aim for is to have a higher ratio of the high-risk areas, the high-risk zones, a higher frequency of testing, both for pathogens and for hygiene indicators. And then sometimes as well, legislation and consequences may also dictate where and when you test for your pathogens. This is also another thing that has to be taken into consideration. If you have to report to authorities, for example, your zone 1 samples, your product contact surfaces, then that may dictate how you arrange your sampling plan as well. But you will see in general, you end up with a number of samples. And another point to make as well, you may, in your routine sampling plan, you may select 20 sampling sites in your production facility for zone 1, but you don't necessarily have to do all of those each week. You may decide on a rotation policy. So I may decide I do 10 per week, but I do 10 of one sampling sites 1 week, and then the next time I'm doing it, I rotate the sampling sites as well. So that's another sort of a change you can actually make within your sampling. So you can have, as part of your routine, a larger number of sampling sites, but they don't all necessarily have to be tested at any one particular time. So then in terms of investigative, this is more interesting, let's say, because this is a supplement to your routine. Your routine should be, this is what is documented. You should have your plan, you know exactly your sampling sites, but then there are occasions when you have to do an investigative environmental monitoring as part of your overall program. And this should be different sites where possible, not the routine sites that you've selected, but it's sites that are, for example, maybe difficult to reach, or sites you can select when you're dismantling key pieces of equipment, maybe once a quarter or once every 6 months, you dismantle certain equipment for a certain deep clean, then this is when you can introduce your investigative sampling. You also can do investigative sampling as a result of a finding. So, you have a finding. If, for example, you have a finding in a finished product, then that will immediately trigger a lot of investigative sampling. So you will almost inevitably see, not to sampling plan, you will go after a lot of different sampling points than you had before, and also you'll increase the sampling in your zone 2, 3, and 4 above and beyond what you have in your routine sampling point. And as I say, you can also introduce what is commonly known now as a swabathon. So it's also a reasonable point to take on board is that, for example, once a year that you really go and you do a swabathon. So you really go with a new pair of eyes, not the normal sampling person. Someone goes to that person and says, how about looking here? How about looking there? Use a different sampling tool, etc., and actually do a swabathon of your factory itself as a supplement to your routine. Because you get used to, remember, it should be an early warning environmental monitoring. So I don't suggest doing a swabathon on a regular basis, but perhaps once a year, it's good to do a deep dive and pick new samples and actually test them. And again, if you have findings in some of these areas, even if it's an E3, if you can supplement that with something like whole genome sequencing or some typing form, then it would be good to identify, do I have some persistence and where are they, and how could they contaminate a low risk area and contaminate a high risk area from a low risk area. And sometimes the forgotten thing in all of environmental monitoring program is the actual real practicalities. How do I take my sample? What tools do I use, and how do I store my samples and get them to the laboratory? Because if you use the wrong tools, it doesn't matter how good your sampling plan is, be it routine or investigative. And if you abuse the sample when you've taken it before it gets to the laboratory, again, you almost undo all of the good sampling plan that you have. So it is really important that you know the people are well trained, they use the correct tools, and you see examples that I've given here about some of the tools that are used. Sponges and swabs is a common one. And one interesting feature is some people use dry swabs, but we have shown many occasions, and other people have as well, if you moisten the swab slightly, you will have a far better recovery from your swabbing samples. So it is a good idea to use moist swabs as well. Then spoons and spatulas is common for residues, where you have lines where you actually have residues of powder, etc., to collect that. Vacuum cleaner samples, as I mentioned before. Syringes for drains or where you have liquid material, or you want a floor if you have a flooding on a floor or whatever, stagnating water point somewhere, then use syringes, etc., to take up a volume of material. And then when you've taken your samples, it is always key, taking them is you have to do it in a sterile manner. You do not want to cross-contaminate the sample that you're actually taking, and you must properly label, store, transport dry samples. I've seen on occasions people putting samples taken from a dry environment, they put it in a refrigerator because they want to send 20 samples together to the laboratory. They put it in a refrigerator and let it sit for 3 days. And you can have condensation, etc. Also frozen. If they're taken frozen, they should be sampled frozen. You don't take this frozen sample and then let it thaw, and you could have growth, for example. If it's listeria, you could have growth, and then you send it to the laboratory. But in fact, you are sampling something different from what you actually took the original sample from. So again, very important, the time between sampling and when you actually do the testing. And another point is around foreign bodies. Don't use inappropriate sampling tools where you actually end up leaving physical hazards on the line. Like glass jars, and you break a glass jar by sampling, or you leave debris from swabs, etc., on the line. This introduces another quality element, a defect that you don't really want. And as I mentioned before, supplementing with whole genome sequencing is really a nice way of actually doing a further deep dive on any isolates that you do get. Then importantly as well is the tracking, trending, and responding. You must have a good system where you are able to, let's say, record the points that you're sampling from, have a nice trending mechanism so you're able to see where I've seen amber. You will have action levels for your hygiene indicators. Obviously, if you have a finding of a pathogen, then it will be a red alert. But again, have your action levels in a database so you know exactly and immediately when you have a deviation beyond that action level. And this allows you to be able to respond. You will have certain rules laid down to say, if I have a finding here in zone 1, I do this. If I have a finding in zone 2, I do this. If I have a recurrent finding across different zones, what do I do? These rules should be laid down as part of your environmental monitoring program. You shouldn't be coming in and asking the person in your laboratory, what should I do? I found this. You should know as part of your routines, what do I do in response to types of deviations across different zoning points? And then you have to be able to do your root cause analysis, of course, and then put in place your corrective actions. What we see in terms of this data trending, a lot of people in the past will use Excels or some format like that. But now what we see is a lot more digital tools. And these are really, really nice tools, because people can actually then link the sampling points, they can link the labeling, they can link that with their laboratory if it's a LIMS system or SAP or whatever other analytical system they have. And I just show you a couple of examples of where this is actually moving now. We do something similar to this in Nestle by actually sort of digitalizing our results. So, I, sitting in corporate Nestle, can see all of the factories globally and actually what the pathogen monitoring or the environmental monitoring data looks like from all factories, because it feeds into SAP, and then we track this and trace it. But you see here, I just see some examples, and this is an exhaustive list. There's Novolize, for example, is one company who actually now has digital tools like this. Biomeria Nutriscience have Enviromap, which is again was a tool that's been around for a long time. You have biotrends as well. This is all software where you can map on your CAD drawings where you're taking your samples, label your samples, and then put the data back into the CAD drawing and see all your different trends. And even a further advance to this is a company in the UK called Luminous, and they've got their software called Tracker. And this actually, you can actually wear HoloLenses. They make a 3D picture of the factory. You can walk around with your HoloLens, and as you take the sample, you can take a picture of the sample that you've just taken, and this is immediately uploaded to the software. So when you go back historically to do track tracing and trending, you can actually look at the picture of where the sample was actually taken at a time point, based on the picture that you've taken in real time. Now, it might sound as if this is a utopia in the future, but this is a direction with the digital tools going now. And I think environmental monitoring lends itself well to digitalization, because in the past, we've seen people collect a lot of data. The data is not clean. There's not good metadata where the samples have been taken, and it's difficult to do tracking and tracing. But with the digital solutions, you're able to track and trace and respond a lot better. And finally, on the note of digitalization, I think everybody probably wears a watch like this now. And I say, this is what the digital tools and environmental monitoring are all about. It's actually taking the pulse of your factory. I refer to environmental monitoring as, like the digital watch. It is monitoring the pulse of your factory in real time, and it allows you to respond appropriately in real time, before you do finished product testing or before you have an incident. So with that, I would like to stop at this point and happy to take any questions. So back to you, either Bernadette or Miguel.
Thank you very much, Dr. Donaghy, for your very interesting presentation. We now ask Dr. Farber, Dr. Goris, Dr. Donaghy to open their screens and take part of the discussion session and answer some questions of our audience. We received a huge number of questions, but the time is short, so I selected one question for each speaker. I would start with Jeff Farber. The question is, with the new eating habits, more ready-to-eat food delivery and takeaways and cooking at home, and more use of food and personal hygiene protocols, certainly because of the pandemic, what can be expected on the occurrence of foodborne disease outbreaks?
Okay, thank you, Bernadette. Very, very good question and very topical now with COVID going on. And actually, there was just some recent studies some of you may have seen coming out of Spain. I think they looked at the number of Campylobacter cases. They had over 1,300 in 2019, and they went down to 391 in the first 6 months of 2020. And so, but you hear both sides of the story, because basically what's happening is that you could have people who are getting sick with maybe not as severe to get to the hospital, but they're still sick with a foodborne illness. They're actually afraid to seek medical assistance because of COVID. So they're not going to see their doctors. On the other hand, you have people cooking more in their homes. So they're cooking more. We all know that in many countries you have, in households, you have quite high incidence of foodborne outbreaks that are related to households. But so you have, again, both sides. You have maybe increased cooking in the home, but I think people are using for now better practices in terms of maybe disinfecting surfaces, so maybe less cross-contamination. But again, on the other hand, you have more takeout foods. So the question is, are the people, and we have these ghost kitchens that are preparing foods. So what are some of the hygiene habits of some of these newer restaurants? So you see sort of both sides of the picture, where you can see a decrease in one instance and you can see an increase in the other instance. So I think we should do further studies to actually look at what effect COVID has had. And I think it'll be important to know as we move ahead into the future.
Yes, Jeff, this is a never-ending story, right?
Yeah.
Okay, thank you very much for your answer. Now, the other question is to Dr. Goris. It says that should utility and indicator organisms be raised as hazards in the HACCP study?
Thank you, Bernadette. I don't think they should. They are not hazards. They are tools that we can use to look at whether our processes are running properly, whether we are taking care of hygiene properly. There are other ways to do that as well. I think John mentioned that sanitation, of course, is a particular thing you would do in your in your GHP process, in your manufacturing operation, and you wouldn't use a hygiene indicator to look at the sanitation. You would look at maybe physical measures or record keeping or what have you. You can have different ways, but if you think about an overall environmental indication, maybe indicators could use, but that's then not a hazard. It's a tool that helps you verify that you're in control of your operation. The hazards would be only moderate, severe, or serious pathogens. That those are the ones that make people ill, and other hazards would be physical hazards, chemical hazards, allergens, but not the indicator or utility organisms. They could be in the hazard plan, but then as tools to verify certain aspect of the hazard plan.
Yeah.
Thank you.
Okay, thank you for clarification. Then the last question to John Donaghy says, there's an important increase of air sampling in food plants to better understand the airflow and possible contamination from air. How do you see such air monitoring as part of environmental monitoring program in the food plants?
Yeah, there's maybe two trains of thought on this. My train of thought is that you control it up front, so you have the appropriate air handling units in place, and they have a certain performance. So you base it on the fact that you put in place your zoning, your air handling with particular filters, G7, F3, etc., different filters depending on what performance you want to reach. We don't do a lot of air monitoring as part of environmental monitoring, because this can actually be quite difficult in a factory where you generate lots of aerosols, even through your manufacturing process. So trying to measure this sometimes can be quite difficult to verify. So in that case, we do less environmental monitoring of air samples, but actually put the emphasis on the measures in terms of the air handling units and its performance.
Okay.
I hope that's clear.
Yes, I think it is. Okay. Well, thank you very much for replying the questions. Well, on behalf of the Latin American Subcommission of ICMSF and my co-host Miguel, thank the speakers for the outstanding presentations and participation in the discussion sessions. The feedback we are receiving indicates that the participants enjoyed the webinar very much. We also thank again our sponsors, 3M and Merck, and the Food Technology Institute and the Food Research Center of the University of São Paulo. Their support was essential for the success of the webinar. It had almost 1,500 registrations from Latin American countries and from other parts of the world. And surprisingly, we had almost 250 persons following the whole webinar without interruption, which is an interesting number. With that, we finish here. We are looking forward to seeing you again tomorrow for the next session. It should be focused on microbiological criteria for product acceptance. And don't miss the session on Thursday when we will discuss myths and facts on COVID-19 in the perspective of food safety. Thank you very, very, very much. Goodbye and take care of yourselves and your beloved ones. Have a good day.
Thank you, Bernadette. Bye-bye.
Thank you.
Bye-bye.
Each time there is a contamination in food or beverages, the public is made aware. What they don't see is you, mitigating risks every day, taking difficult decisions and making our food as safe as possible. Because you take your job as seriously as we do. With over 350 years experience in highly regulated industries, we understand the importance of reliability and efficiency in your lab. So be it to verify existing methods, stay on top of changing regulations, or to adopt the newest technologies. You can find it all on sigmaaldrich.com. Tailored products for each step of your workflow available on our website. We have products that are suitable for microbial and analytical needs in the crucial step of sample preparation. We have solutions for the most routine sample analysis to advanced genetic detection, such as the Assurance GDS for rapid pathogen detection, often used to test for E. coli in beef. And we support you with a complete set of services and specialists. Our experts are here to improve your day-to-day work with 4 dedicated portfolio brands: Millipore, Sapelco, Sigma Aldrich, and MilliQ. All these products can easily be ordered on our website so that you can focus on making sure that every sip, every bite is safe because it's been tested by you.